My name is Richard Furr, and I can say I am cloud hired.
That yes, come and join and get cloud hired. I'm cloud hired.
I'm cloud hired.
I'm cloud hired.
Hey, Go Cloud Architect family. I'm cloud hired.
So I'm cloud hired, guys.
So I'll just say I'm cloud hired.
I'm cloud hired.
I'm cloud hired thanks to Go Cloud Architects.
It worked for me, and now I'm cloud hired. Because of Google Architect program, I am cloud hired. See!
I am cloud hired. Thank you, Mike and the GlowCloud team.
Welcome back, everyone. We are back after our break for part 2 of our completely free AWS Advanced Networking Bootcamp. We had some fun this morning. We talked a little bit about the AWS Cloud. We talked a little bit about the VPC. We had a little bit of fun going over some routing and how routers work and what switches do and a little bit of VLANs. And now we're back for the second half. If you've just joined us, please download the completely free AWS Advanced Networking lab demos. Here's the reason why. We have a very ambitious schedule for the next 3 days, and we have a tremendous amount of labs. Quite frankly, we have almost 2 full days of labs. Labs on AWS, labs in the data center, labs on routers and switches to truly make sure you get the understanding of the network beyond what you could just do in AWS. So sign up and get your free AWS lab demos now. They're in the chat box on the description. If you're back, please give me a hashtag AWS Advanced Networking. And that way I know you're awake, alert, and oriented. So we're going to get back to the content. Mo is going to get back to some really cool content. He's going to start talking about encapsulations. We'll hear about transit gateways. We're going to get into all kinds of fun stuff. Mo's got a lot coming for you. And maybe you'll hear back from Benedict or me today. I'm sure you will in the questions, but Mo's got a lot of content. And then tomorrow, back at 10 a.m., we got all kinds of exciting networking content for you. As you can tell, I love networking, along with my team of network experts over here. And then we'll be back again on Sunday. So let's make it a great experience. We'll go for a little while. We'll answer your questions, have some fun. So welcome back. AWS Advanced Networking Day 2. It's for the ANS-C01 exam. And this is our full AWS networking specialty course available at no charge to you from Go Cloud Careers. So you know me. I've been a network architect for 25 years, in case you haven't joined me. We're here with Mo, who's a network architect and a CCIE with more than 10 years experience. Benedict, who's a great network architect with more than a decade of experience. And of course, Mark on our team was part of this, and he's another network architect with over 10 years experience. So lots of fun. So Mo, let me turn it back over to you.
Can everybody hear me? Okay, I think everybody hears me now. All right, so we got some exciting topics for you today.
I forgot to unmute you there, Mo. I'm sorry.
No worries at all. All right, so we're gonna start with encapsulation, encryption, underlay and overlay networks, GRE and VXLAN, right? That's a lot of topics. Trying to fit together because they're very closely related, right? Most of these topics are very closely related. So let's start with encapsulation. What is encapsulation, right? We've already spoke about encapsulation a little bit, so you have the basic premise of what encapsulation is. But all what encapsulation is adding layers to your traffic, right? So you're trying to send some data from point A to point B, right? And I'll show you a good visual representation, right? So you have data that you want to send from point A to point B. In order to be able to send that data, right, you need to encapsulate that data with information, right? It's almost like you have a letter you want to send to somebody, right? You have to encapsulate it in an envelope, right? You need to write their address, information, and so on and so forth. It's kind of the same idea, right? So you have your data, which we call the payload, right? You have that data, then you want to send it from point A to point B. You need some sort of a protocol that facilitates that transportation, right? So that's where you use the TCP or UDP, right? The TCP or UDP header. That's layer 4. Then you need an IP address, right? A source IP, destination IP, almost like a phone number or an address, right? So that IP address, that's at layer 3. That's another encapsulation, what we call a header, right? And then you want to send it over layer 2, right? Meaning you actually want to send it through the line, right? Or the cable from point A to point B, right? And in that instance, you want to add a layer 2 encapsulation, which what we call a frame, right? If you're using Ethernet, then that's an Ethernet frame at layer 2, right? And of course, then it's just a physical zeros and ones, right? Actual digital signal that you send it through the cable, which is, the line card, which is the physical layer or layer 1. So that's basically at a very basic level, that's what encapsulation is, right? So you can see it's the process of adding a layer of information to the payload, right? The payload is the actual data to be able to carry that data. So as you can see, encapsulation is very important, and it almost pretty much touches every other subject in the networking realm. Now, just like I said, Ethernet is a very common layer 2 encapsulation, right? Also, we have tunneling. We spoke about tunneling a little bit, right? IPsec is one form of tunneling, right? It's encrypted tunnels. So an IPsec tunnel, which is encrypted most of the time, in order to be able to send an IPsec packet, you need to add an extra tunnel, and then you need to add an extra encapsulation before you encrypt everything that is encapsulated inside that tunnel. Okay. So with tunneling in general, and this is not just for IPsec, there's a lot of different tunneling protocols, right? And tunneling protocols in general, right? If you have, we're keeping it simple. So we're talking about 2 nodes, point A and point B, over the public internet, right? So there could be 20, 30, maybe 100 pass by to get from A to point B over the public internet, right? Now, in this instance, right, you typically have a public IP on your router, right, on both ends. Let's call this IP X and Y. Okay, that's the public IP. You want to establish a private tunnel, right? For example, you have your private network here, Okay, you have your private network here. And let's say behind this, you have a 192 network, like a private network, right? And you don't want to use NAT to go through the public internet. You don't need an actual direct access, layer 3 access between those 2 private networks. This is where tunneling can be useful. What you would do is basically establish a tunnel over the public internet, and over that tunnel, you can use network address translation. So this is very useful in cases where you have two sites and you pretty much own both sides, right? And then you want to send or tunnel your private data over that tunnel, right? So in this scenario, we said we have A and B. Let me try to, okay. So you have A and B, right? You have the IP, public IP here that is X. Over here, you have the public Y, right? The way tunneling works, if you think about it, right? You have your payload. Let's say you're sending data. You have your payload, and then your, let's say, TCP header, and then you have your IP header. Let's focus. So you have a source IP, which is source IP of X, because you're sending data from A to B, right? The destination is Y. This is Y, right? Now, these are the public IPs, right? So what if I wanted to send data? Bear with me 1 second. What if you wanted to send data instead of using X and Y? Give me 1 second to try to. And that's not the most ideal way to draw. But let's say you want to send data from 192.168, the network here. Let's say this is a private IP, which is 192.168, and you want to send your traffic to 172.16. So another private subnet, right? But because if you send this traffic without actually encapsulating or tunneling that traffic, you're going to end up with the issue that once you send the traffic out, right, it's just going to be dropped because you don't own that. You don't really, a 192 address and a 172.16 address, right? Those addresses are Class C, they're private. So you can't really use these addresses, well, not Class C, but, RFC 1819. So they're private IPs, right? So they're not meant to be sent over the public internet, right? Everybody uses the same IPs, right? And so if you want direct access between those two private subnets, right? So let's say the source here is the 192, right? 192.168.1.0. And over here, the IP is 172.16, which is the destination, right? This right here. In order to traffic, you need to tunnel it or encapsulate it by adding an extra header. So this is already, and in this header, you're saying the source is X, the destination is Y, right? So because the internet already knows how to reach X and Y, every node along the path knows how to reach X and Y, right? So as you send the traffic, that's why we call it tunneling, right? Everybody says, okay, the source is X, but we're focusing on the destination, it's Y, right? Everybody knows in order to reach Y, go this way, right? Once B receives that information and it sees that it's intended for B, B will decapsulate this information or take off this header. It will look at the rest of the information. It will see that there's another IP header, layer 3 header, which has a destination of 172.16, right? It will send it to that the other way around, just switch the IPs associated with the destination. So that's tunneling, right? So obviously it's very useful. Bear with me as I. So that's encapsulation. One of those encapsulation methods, there's a lot of protocols, V protocols, that allow you to do encapsulation, tunneling, right? And one of those protocols is GRE, or generic routing encapsulation, right? It's a very light or encapsulation protocol, so it's very easy to implement. It's not CPU intensive, right? It's a light header, and so all what GRE does is encapsulates your IP packet with another IP header, right? Just like we described, all right? Just as we described here, you're adding an extra header, which is the overlay, right? So what we call the underlay, right? So very quickly, let's go through what before we get deeper into GRE. Let's discuss what is an underlay and an overlay, right? The underlay is basically the actual internet, right? The infrastructure that you're using to go from point A to point B. So that's the underlay, right? In our case here, in our scenario, right, we're using our DIA, or direct internet access circuit, right, to exit out to the internet. So my underlay IP is the IPX, right? My source, my destination is the other side is Y. So that's my underlay. That's the infrastructure I'm running the tunneling on top of. The overlay is the encapsulated IP. It's the hidden IP, right? The IP that will only be seen between point A and point B, right? And when I say seen, this is not encrypted, at least as of now. So when I say seen, I mean who actually wants to interact with that encapsulated IP in a meaningful way, all right? So in this case, the 192.168 IP and the 172.16, those are the IPs that are actually encapsulated inside that tunnel, right? So you can think of them as the overlays. But in general, think of the word underlay and overlay. The underlay is the actual, let's say, the infrastructure, and then the overlay is what is built on top of that, right? But you need the underlay in order to facilitate that transportation from point A to point B. Okay, so GRE, right? Genetic routing encapsulation. So what GRE does, it takes the actual frame, right? It takes the actual, or not the actual frame, but it takes the actual header that you're sending from point A to point B. And what it does is adds an extra header on top of it. So you would add an extra IP header, right? And that extra header is, in our scenario previously, is the IPs of the public internet, right? The X and Y. So we can say that GRE is an encapsulation protocol or a tunneling protocol, right? That helps us establish a virtual private line, virtual private network from point A to point B, right? It's a point-to-point tunnel, or a point-to-point VPN. Okay. So in order to accomplish that, we're using a GRE header, right, that carries the tunnel's data or metadata, right, the actual information that is needed for the tunnel to actually function on both ends. Now, besides GRE, there are other encapsulation methods that can be used. GRE is one of them, right? Then we have IPsec. IPsec is both an encryption and encapsulation method, but it can be used only for encapsulation, right? It's not typically used, but it can be used just for encapsulation. Now, IPsec is a method of encapsulation. MPLS, or multi-protocol label switching, right? This is more of a a service that you buy from a internet service provider, right? Layer 2 tunneling protocols, right? Each one of those protocols has a unique way of doing its encapsulation, but it's still encapsulation nonetheless, right? As we discussed, you're adding layers, just like you would send a message, you add an envelope, you're adding layers to that data in order to be able to send it smoothly from point A to point B. Okay. Now, tunneling the traffic is great, right? And you'll be able to send your traffic from point A to point B over the public internet. The problem with that is that if anybody can eavesdrop on your data, basically anybody can read that header, right? If you run an actual a packet capture, you'll be able to look at that data and actually, investigate and see what's inside that header, right? Obviously, if you're using HTTPS, you can at least encrypt the data, the payload side of that, right? But what if you're running a protocol that doesn't encrypt your data? Or, what if you don't want people to see your overlay IP, right? Remember we have private IPs. So there's a lot of information that is just sent in clear text, and anybody can capture that traffic and see it, right? So if you look at the slide here, right, encryption is a method, right, that can help with that. And what encryption is, it's basically the process of encoding information, right, or ciphering that information so that nobody can understand that information unless they have the decryption key or a key to decipher that information, right? So encryption is a very old, it's not something new, right? We had encryption for probably 1,000 years or more. It's just, encryption is getting more advanced, and, as hackers and bad actors, learn how to decipher, and, as technology advances, we create more advanced encryption methods, right? But at the end, encryption is a way to cipher your traffic, right? So you send your traffic and you encrypt it in a certain way with a key or an algorithm, so that only the receiving end, the intended receiving end, is able to decipher or decrypt that information, right? So if somebody eavesdrops on that information and they don't have the actual key, then all they're going to see is just gibberish, nothing meaningful, right? So as we said, encryption and encapsulation work hand in hand, right? For example, if you run GRE over the public internet, more likely than not, you want to add an encryption on top of GRE. So you can run IPsec encryption or IPsec tunnels on top of GRE. Okay. So another thing with encryption, as we said, encryption is nothing new, but the encryption methods and protocols that we use, right? These methods keep on progressing, right? So an encryption that was secure 10 years ago or even 5 years ago is not secure today, right? For example, MD5, right? Pretty sure that MD5 can be broken easily now in today's age, but not 15 years ago or 10 years ago. So encryption methods, as computer power increases, as with AI and different advanced algorithms, right? Encryption needs to be up to date, so that you need to always make sure that you're using the encryption methods that are still considered secure, right? Now, there are many different types of encryption, right? But as far as the mechanics go, there's two different, let's say, methods of encryption. One is called symmetric, and another one is called asymmetric, right? And it's very simple. The idea behind symmetric encryption is that you're using the same key for encryption and for decryption. Hence the name symmetric, right? You're using the same key. So let's say you have point A and point B, right? They have a key. Let's say this key is X, right? And this is a key, right? So you send the traffic and you encrypt it with this key, which is X. Nobody can read it unless they have this key. Once point B receives traffic, since it has the key X, it can use it to decrypt that traffic. So the same key is used for encryption and for decryption. Now, asymmetric encryption is different, or asymmetric keys are different. With asymmetric encryption, you're using one key for encryption and another for decryption, right? A very common use case for asymmetric encryption is what we know are PKIs, or public key infrastructures, right? Like right now, you're using a web browser, right? Your traffic is encrypted, right? You establish a secure connection over HTTPS with let's say, Google or any website, right? You have access to the public key. Now, the server encrypts the traffic with a private key, and the private key can only be encrypted with the public key, right? So you know that the information is authentic because, and let's use Google as an example, right? Because the traffic can only be encrypted with the private key, and nobody has access to the private key except for Google. And so when you receive that traffic, you can decrypt it with the public key, right? But you can't encrypt the traffic. For example, a bad actor can't, just having access to the public key, there's not a lot they can do with that public key except for just decrypting the traffic, right? So that's a use case of asymmetric key encryption. Now, asymmetric key encryption is very resource intensive, right? You need one key for encryption, another key for decryption. So typically it's used initially to establish authenticity. And then once that is established, the actual data is sent using symmetric encryptions, right? Like AES, right? Now, RSA is asymmetric. AES is symmetric. Now, just that, seeing AES, that doesn't mean AES is any AES encryption is secure, right? Encryption is the bigger the size of the encryption, the more secure it is, right? So AES has different, let's say, different versions, right? As you move up, it's more secure. Same thing for RSA. Okay. Let's go to the next slide. Okay. HTTPS, right? As we said, right? HTTPS is one method that uses asymmetric encryption, right? But it's used just initially to establish authenticity, right? So the public, during the initial handshake, right, to establish that the server is, the actual authentic Google server, right? But once you start sending the data, that's when you start using symmetric encryption, because it's much faster, much more efficient, although not as secure as asymmetric. Okay. Okay. You probably hear a lot the word SSL, TLS, right? SSL, or Secure Socket Layer, is the successor of TLS, which is Transport Layer Security, right? My apologies. TLS is the successor of SSL, right? So you can think of TLS as SSL version 2.0, right? But they have the same basic premise, right? It's an encryption. It's a method for encrypting your traffic, over the transport layer. So this is not a layer 3 protocol, SSL and TLS, right? It's a transport layer protocol. Now, IPsec is another example of encryption, right? IPsec is very commonly used, right? We say IPsec is a layer 3, encryption because you're encrypting your actual header, right? Those protocols that we discussed so far, encryption protocols, these protocols are used in transport, meaning as you send traffic from point A to point B. But there are different other types of encryption. For example, data at rest encryption, right? For example, you have your hard drive and you have data and you want to encrypt that data, right? That's more of a data at rest encryption, right? You still want to have your data encrypted as a store so that if somebody gains access to that storage, they can't read it, right? And there's many different methods for encryption, encrypting data at rest. One of them is full disk encryption, or FDE. Okay. VXLAN. What's VXLAN? Right. VXLAN is another protocol that establishes, let's say, encapsulation, right, or tunneling. What VXLAN does is it's a layer 2 encapsulation protocol, which means it can carry layer 2 information or stretch your layer 2 domain or broadcast domain over the public internet, or technically you wouldn't use it over the public internet, but over an IP or layer 3 infrastructure, right? So let's say you have So let's say you have your data center, because it's typically used in a data center, right? Let's say you have your switches, right? Let's say you have a server here. And we're going to keep it really simple, so we won't use a very basic example, right? I know I say switches, but these are, we're using these are layer 3 switches, which means they actually route traffic, right? So you have your infrastructure, you have server A and server B, right? Let's say server A is in network 192.168.1.0/24. Let's say over here you have server A, which is on the same subnet. You want it to be on the same subnet, right? Let's say it's on the same subnet. Let's say this IP, this server has a .1 IP, this server has a .2 IP, right? Well, they're in completely, because they're separated by layer 3 domains, right? It's impossible to send, they're not in the same, broadcast domain, right? So you need a method to, if you wanted them to be on the same broadcast domain, you need a method to allow server B to communicate directly with server A without having to route that traffic, right? Well, one method is obviously not practical, but you could just add a layer 2 switch and just connect it, right? But that's not practical, right? Especially what we're trying to establish here is keep the existing infrastructure, but also establish some sort of a layer 2 domain or a layer 2 end-to-end connection. What you can do is use VXLAN, right? And what VXLAN does is it encapsulates your layer 2 traffic over layer 3 so that you would send your header, or you'd send your packet or tunnel it from this server through this switch all the way to, or layer 3 switch to this layer 3 switch. Once it gets here, decapsulates it, you get the layer 2 information. So it's similar to what we discussed with GRE, where you have a layer 3 encapsulated with layer 3, but in this example, you have layer 2 encapsulated with layer 3. So it's very useful, especially for especially for a data center environment, right? Because you have different type of workloads. Without going into too much details, there's different workloads that might require you to stretch a layer 2 domain. For example, if you're familiar with VMware, if you want to do a vMotion, or you transfer a server from one side to another side, you're going to need a layer 2 end-to-end, right? And this is where a VXLAN can be very helpful. Now, VXLAN is a good encapsulation method. The benefit is that it's very lightweight, it's very extensible, right? Hence the name Virtual Extensible Local Area Network, right? Also, there's other benefits from the data center side, right? For example, allows you, obviously, number one, it allows you to stretch layer 2 over layer 3. VXLAN has 2 to the power 24, I believe, or 60 million VXLAN IDs versus pure layer 2. If you wanted to have layer 2 connections end-to-end in your data center, right, you're stuck with 4094 or 4095 IBs, VLAN IDs, right? Which for large-scale environments like AWS, let's say AWS data centers, right, that's not enough. This is where VXLAN can be very useful because it allows you for a more extendable layer 2, let's call them VXLAN IDs, which is a layer 2 domains, right? So instead of 4096 or 4095, really, you get up to 60 million something, let's call them VLAN IDs, right? Okay. So what's the use of VXLAN, or why is AWS using VXLAN, right? Well, primarily, AWS uses VXLAN as an layer 2 encapsulation method for traffic mirroring, right? And all what traffic mirroring is that what you're doing is, let's say, and I'm gonna look, I believe I have a good diagram to explain this. Yeah. So traffic mirroring is sending your capturing your traffic from an instance and then sending that traffic to a device to store that information, right? So for example, let's say you have a device, or let's say you have a server that does inspection of data, logs the information, or maybe just saves it for whatever policies that you have set in place in your organization, and you want to record all your traffic that exits a certain EC2 instance or machine, and you want to send all that traffic for logging or monitoring, right? That's where mirroring can be helpful, because if you think about it, let's say you have, as shown in this example, let's say that you have the source A, right, and another source B. So these are 2 different, let's say, EC2 instances, right? And you want to send that traffic so that anything that enters this source, or let's say anything that exits this source, you want to record it and send it to some server, some target, right, for logging. Now the way you want to send this traffic is you want it to be layer 2 end-to-end, right? Or AWS intended method is they want it to be sent as layer 2 end-to-end, right? From the mirroring source to the mirroring destination or the target, right? That does the logging. AWS uses VXLAN encapsulation for that reason, right? Because what happens here is that you have the original packet, right? What VXLAN does, or what AWS does, they add the VXLAN header, they reserve the layer 2 information, and then you have a new source and destination IPs where the source IP here is the actual mirroring source, and destination is the server that does the logging or the mirroring target or destination. Right. So that's the use case for mirroring in the context, or the use case of VXLAN in the context of mirroring. And the reason why they're using VXLAN is because VXLAN is very extensible, right? It has a lot of, your number of IDs that you can use within VXLAN is much higher than any other encapsulation method, right? And another thing is because it's, aside from it's extensible, it's there's a lot of metadata that you can add into VXLAN. Okay, let's take a break and take some questions.
All right. So thank you all for that. Now, this is some of the deepest and heaviest content during the entire program. So thank you all for being strong. Thank you all for sticking with this. This is some heavy duty networking. The evolutions of this encapsulation are very old. We'll give you some examples as you go through. We'll answer some questions and then we'll get into some other stuff. But you may need to watch this once or twice. That's okay. We're going to leave this on YouTube for you. We want you to be helped as much as possible. So we're going to go through questions one by one. If you just joined us and you didn't know that we have an incredible number of free labs, almost 2 full days worth. And I mean, about a day is a little more than a day and a quarter is there now, but we're adding more by Sunday for you. Download them. They're in the description of this video as well as in the chat box. We definitely want to help you with that. So take advantage of those, get those labs along the way. Now let's get to some questions.
Okay. Okay. So first question, I think it's the opposite. Public key is used for encryption, but only the private key can decrypt the information. I believe it's actually public key, because if you think about it, right? Private key, public key is what you share with all the clients, right? So me in my browser, I have the public key, right? So I use it from my end, I use it for decryption, to decrypt the traffic that I receive from the Google, as we said, as an example, right? But I'll let Benedict speak on that.
And I can help with this one as well. You want to go, Benedict, or want me to do this?
So can you hear me?
Yeah.
Okay, so there are different concepts here. When we're trying to enforce the concept of confidentiality, right? You're going to encrypt the message with the public key of the receiver. And then when the receiver gets the message, he'll decrypt the message with the private key. Okay. When you're trying to enforce the principle of integrity, you encrypt the message with your private key and then send the message to the receiver. And then when the receiver gets it, it decrypts the message with your public key. So there are 2 different concepts here.
Exactly, based upon what we're trying to do. A good question.
Yeah.
Let's go to the next one.
Okay. So is it safe to say that VXLAN is a multi-layer protocol, layer 2 and layer 3? Also, notice I'm calling it a protocol. Is it really a protocol or just a service? I would say it's a protocol.
Protocol.
It is layer 3, and it depends on what. So when we say layer 3, it's because it works over layer 3, right? But you're encapsulating layer 2 traffic. I hope that answers your question. I think the short answer is layer 3, but the VXLAN header itself is also, has a header in layer 4 as well. So really, like as we alluded to previously, is that the OSI model is not like clear and clear cut where you follow it word by word, right? It's more of a method to establish like a common grounds or a language so we all can understand, but it can get vague sometimes. Depends on the protocol that we're in question.
Yeah.
I think that's a comment.
Yeah, we're going to work on that since we don't know what it is, Muhammad, out of context. Let's go to the next one. Okay, so let's talk about that encapsulation thing a little different and the GRE tunneling, because, and yeah, we can definitely mention some good books and network fundamentals, but I want to talk about this. Where did all this tunneling stuff come from? It came from a long time ago when we had an IP network and we used to have these other networks like Novell and AppleTalk, and we wanted to push the AppleTalk and the Novell traffic over the IP network. And thankfully that stuff went away. I don't miss that stuff. It was a long time ago. Those other networking protocols, and it all became IP. But anytime we want to push something through something, wanted to create a transit between two clouds and push IP multicast in manners that they don't allow you, and you can do multicast, but you can't do everything, you can just tunnel it through. So think of tunneling as anytime you've got something that you need to push through something else, because either you need to hide the IP addresses, you got stuff that's not routable, you've got IP addresses that aren't routable, and I hope that makes sense. And the way I look at encapsulation, it comes back from my medical days. If I was going to give a patient amoxicillin, it comes from it comes from the manufacturer in powders. I could just pour the powder on them and say, try to take it, right? Or I could give them powder and they could pour it into their coffee and drink their coffee. Or the drug company could take that powder, put it in a capsule and say, here's the capsule, take the capsule. It's easier to transport a capsule. It's easier to take the capsule. And that's really the whole point of encapsulation. Put something in something else and make it a lot easier to send. Hope that helps. Good book on networking fundamentals. Well, yes. So here's what I will tell you. There's one book that I find excellent on basic intro networking concepts. Every Cisco certified internet expert has read it. It's from Addison Wisely. It's TCP/IP illustrated from Richard Stevens. If there's a network architect out there, they've read it. That gets into some very intro level network fundamentals. I will tell you the Wendell Odom, I think it's Odom, the CCNA books are very good. I will tell you the Routing TCP/IP volumes 1 and 2 from Jeff Doyle are excellent. I will tell you the book Internet Routing Architectures from Bassam Halabi are excellent. I will tell you can go to the IEEE and read all the Ethernet specifications completely free. And that stuff's good, Ethernet Wi-Fi. And I would tell you to go to the Internet Engineering Task Force and read the RFCs for OSPF and DNS and BGP and all those other cool things. So that would be from me. And I'd say that's some good fundamentals. But, Mo and Benedict, do you have any other fundamentals you'd recommend?
I think you mentioned the really, really good books. If I were to add one book, it would be, actually two, would be Routing TCP/IP, Volume 1 and Volume 2. But yeah, I mean, if you want to get into like really advanced routing and how routing works, I would definitely recommend Routing TCP/IP.
Yeah, for the fundamentals, I like the CCNA book. It's well detailed and gives you everything you need to get started in the world of networking.
Can I please summarize VXLAN? So I've actually not worked with VXLAN, so I'm going to have either Benedict or Mo explain that one to you. Because I know what it is, but I don't want to be inaccurate.
Yeah, okay. So to summarize it very lightly, right? And somebody asked a good question there. Why would I use VXLAN or instead of just sending the data from point A to point B, right? Because there is a layer 2 header there too, right? But what if you want to reserve that same layer 2 header? Because if you think about every hop along the path when you send your traffic over the public internet or over any layer, multiple layer 3 interfaces, right? You're going to change that header. You exchange the source MAC address and destination MAC address. You're going to keep changing it, right? VXLAN allows you to keep that same MAC address from point A to point B, even though those 2 points are so far away, right? They can be multiple hubs away. You keep that same source MAC address and destination MAC address, right? So that's where it helps. You keep the same broadcast domain. That's different from a layer 3 tunnel. I hope that answers the question. It is a very kind of like a dense topic, right? But we wanted to kind of cover it, at a fundamental level. I hope that answers the question.
You mentioned Todd Lamley's, that's fine. For CCNA, we recommend official Cisco documentation, which is the Cisco Press books, since they make the exams. There's a lot of good, King, there's a lot of good books out there. I've not read that one. I haven't done a CCNA since, 25 years ago was when I did my CCNA. But I'm with you on that. But there's lots of good opportunities there. So let's get back to the content. We'll turn it back over to you, Mo.
Okay.
Give us a hashtag AWS Advanced Networking so we know you're awake with all this hardcore networking stuff. I kind of love it, but I like networking.
Okay. Over now is software-defined networking. This is a topic that we have a video on YouTube, I believe, that covers this, right? But let's dive into what is software-defined wide area network, or SD-WAN, right? SD-WAN is all it is. It's a method or a practice of simplifying networking, right? In our traditional networking, right, we have, let me backtrack a little bit, right? Let's say 10 or 15 years ago, most of our traffic was heavily centralized, right? Most of your traffic was branch to data center or branch to branch. So most of your traffic was heavily centralized within your organization. And there was very few services that you use, for big organizations, that you actually use the public internet to access, right? So most of your services and applications were local, were over between your branches or data centers, right? This is changing, right? One evidence for that is the cloud, right? The cloud, you can be working from home and using Teams, and Teams is on the cloud, right? At somebody's cloud or somebody's data center, right? So as you can see, there's a lot of tools that we use today, right? It could be Teams, it could be Slack, it could be many different applications that you're using that are available in the public cloud or on somewhere on the internet. So the type of traffic changed, right? And that adds a lot of complexities. It means that a lot of your traffic that you used to be able to monitor or rate limit or do different things on, right? They're not set in stone. They're not static, right? They change. You add and remove new applications. The actual application you use yourself, it can move from one data center to a different data center. So the whole realm of sending traffic, or the whole realm of traffic flows changed. So SD-WAN can be very helpful for that, right? And all SD-WAN is, it's what we call software-defined networking wide area network. It's a software-defined way of almost like reinventing our traditional routing, right? And with SD-WAN, right? In order to explain SD-WAN well enough, we have to take one step back and talk about traditional routing, right? Or traditional networking. With traditional networking, we sometimes call distributed networking, where you have a router, right? Let's say this is router A. You have another router, which is router B, right? And router A has a management plane, which means it has a method for you to log into that router and manage that router, right? So that's what we call a management plane, right? There's also what we call a control plane, right? The control plane as the name implies, that's what controls the router. These are the protocols. We talk about the different router protocols like BGP and so on and so forth. These are the control plane protocols, right? And then there's the data plane. The data plane is the actual forwarding of data from point A to point B, right? Each device would have the same thing. It would have the management plane. It will have, well, I should be sharing my screen. Okay, sorry about that. So what I was saying, as I was saying, right, you have, with traditional networking, we call it distributed or distributed networking, where your router would have the management plane, right? That's what you use to manage a router. The control plane, this is what actually controls the routing protocols that you use, right? So if you have two routers here, let's say you want to run BGP between those two routers, then you would need some sort of you would need a control plane, right? And the control plane controls the actual routing between those two routers, and it's a session and so on and so forth. So that's the control plane. And then you have the data plane. The data plane is the forwarding of the packets themselves, right? So it's the actual forwarding of the actual packets, right? One good terminology I've heard before is think of the control plane as the highways to reach from point A to point B, but think of the data plane as the actual cars, right? So it's the actual forwarding of the traffic. That's one good way to look at it, right? And so, as you can see, if you have as networks grow, as organizations grow, right, 20, 30 routers turn into thousands of routers, right, and switches, right? So it can get really, it can get out of hand, right? The management can get very difficult, right? And there's different automation methods that you can use, but still, you're still pushing configuration and managing configuration by pushing configuration into different devices, right? Which can be complicated, right? SD-WAN, or software-defined networking, wide area network, is a method of controlling, of simplifying the management and configuration of your routers, right? Or edge devices. We call them edge devices because typically with SD-WAN, we focus on devices that are at the edge of your network, the devices that connect your site or data center into other sites. So SD-WAN, the first thing it does is it takes the control plane. If you remember, we spoke about the control plane, and it centralizes the control plane. What I mean by centralizing the control plane is you take the control plane, instead of having one control plane inside each router, you would have one device, almost like a brain, that takes on information from each edge device or router, and then it makes the control plane or routing decisions, and then it would send that information or instructions to each router, right? And that's what the control plane is, right? So SD-WAN, one of the main features of SD-WAN is having a centralized control plane that takes care of the actual routing decisions at a higher level, right? Another very important feature of SD-WAN is a centralized management plane, right? Instead of having to individually go to each device and manage it individually, you'll be able to go to this one controller, right? And then from that controller, you'll be able to manage all of the devices and push your instructions to all your devices, right? So that's where the management plane, centralized management plane. Now the data plane remains inside the routers because you still need the routers to actually make the routing decisions, right? It wouldn't be very practical to rely on a centralized controller to make those split-second data plane or those split-second routing decisions, right? So the data plane is still distributed across routers, right? But those decisions are made based on the control plane, which is used by, these instructions are sent by the centralized brain or centralized controller, right? So we talked about centralized management plane. We talked about centralized control plane, but a distributed data plane. Well, typically with SD-WAN, there's another component, right? Or another controller. We call it the orchestration plane, right? And what an orchestration plane does is that helps you set up a new device initially, right? So you have a new router, you plug in that new router, and you want that router to connect to the controller, the centralized brain, right? And the way to establish that is using an orchestration plane, right? So typically, or a lot of vendors, what they do is they have a hardware embedded certificate on the router itself, right? And the serial number. And then once you plug in that device, all you need is just an IP on that device, right? You can even get it through DHCP. That device then will talk to home, which is, let's say if it's a Cisco device, it will talk to Cisco's data center. Or if it's a Palo device, it will do the same thing, right? Or Prisma, it will do the same thing, right? But what will happen is your device will talk to, it will call home, what we call calling home, right? It will find, and then once it calls home, right, your controller, because your controller has information of the hardware embedded certificate on the hardware itself and the serial number, it will be able to enroll that device with little to no visible or manual interaction with the device. So all you need to do is have that information of that device, and it will automatically enroll. And once the orchestration plane takes care of that, it will enroll it into your management and control plane, right? This is what we call a zero-touch provisioning, right? A zero-touch provisioning is where you don't have to touch the device. You just plug it in, and it enrolls. And then from the centralized management plane, you can push configuration into ultimately into that new edge device, right? So that's what a zero-touch provisioning is, and that's one of the features. If you come from the world of voice over IP, you might have heard of zero-touch provisioning, one-touch provisioning, right? One-touch provisioning is when you add some basic information and then let the centralized controller take care of the rest, right? It's the same method or the same terminology that we use in voice over IP, in the voice over IP practice, right? We're using the same method for SD-WAN. Okay, so we talked about the centralized control plane, centralized management plane, but the data plane is still distributed, right? And then we have an orchestration plane. Now, depends on the solution, right? There's plenty of solutions, right? I don't even keep up at this point, but there's tens of SD-WAN solutions out there, right? But depends on the solution. Those different controllers, as we said, the management controller or the management plane, the control plane controller, the orchestration plane controller, they can be all in one centralized compute or centralized controller, or they can be distributed, right? And there's a case to be made for either one, right? Like you can say that when they're all centralized, right, it's easier to manage from one place, but you can also say that's a single failure domain, right? Because sometimes all you need really is just the controller once you push your configuration, so you can survive without the management plane, right? At least for some time. So that's some of the decisions as you think about as you choose your the flavor of SD-WAN for your organization. That's one of the questions that you ask, and that's some of the decisions that need to be made, right? But with SD-WAN, ultimately what you're doing is you enroll a device, right? If everything's set up properly, you can use zero-touch provisioning. It calls home, it enrolls with your controller, and then you push the configuration from that centralized controller. You have configuration templates. You just add the information that is relevant only to that site, like for example, the IP address, right? Host name, the site number, things of that sort, right? To signify that one site. And you push all that configuration to that device, right? And then from that controller, you also can push the encryption information to establish IPsec tunnels. You can instruct that device to either establish IPsec tunnels with, let's say, with a centralized hub, like a hub and spoke, or you can do a full mesh. These are all things that you can configure from a centralized place instead of having to go to each device individually and configure that device, right? So it's almost has that automation aspect inherent to this solution, right? Okay. We covered the centralized management plane. Okay. This diagram, if you look at if I share my slides, this is a simple comparison of traditional WAN versus SD-WAN, right? So to the left, right, you have your branch offices and you have an HQ office or headquarters. Let's say it's a data center, right? And each device, each of these routers, right, holds all the management plane and data plane information. And in order to establish, let's say, secure tunnels over the public internet, or you can use some sort of a solution, let's say like MPLS, right, where you basically move the tunneling decision, or you move that decision to the service provider and they take care of it. But at the end of the day, you still have multiple devices that are, it gets very cumbersome to manage individually, right? And if you're going to use something like MPLS, well, it can help, right? Because the service provider will take care of managing that MPLS infrastructure, right? It's their infrastructure, and they would give you end-to-end access between all your sites. That can get very expensive, right? Plus, you don't have a lot of control over that MPLS infrastructure, aside from just having it, receiving your different site information from one branch to another branch. With SD-WAN, right? Number one, it can save you money by establishing an easily maintainable private infrastructure, which is a bunch of private VPN tunnels over the public internet, right? It's easy to maintain, right? Obviously not as easy as MPLS, because MPLS, the ISP takes care of it, right? The service provider takes care of it. But at least with SD-WAN, it's easy to manage, right? So you get some of that, ease of use, right? Because it's very easy to manage and maintain an SD-WAN solution, right? Of course, we have the centralized controller that takes care of all the routing decisions, so that gives us more of the ease of use, right? But you can save some money by not having to use something like MPLS, right? Because if you wanted to establish the same infrastructure that you have with SD-WAN, which can be done, if you wanted to establish the same infrastructure that would be done with SD-WAN, if you wanted to establish it using traditional networking, it's going to be much more difficult to maintain and actually build, right? And that's really where the true benefit of SD-WAN is everything that's done with SD-WAN can be done with traditional networking. It can be done, right? But with traditional networking or traditional WAN, it can be very difficult to maintain. You're going to need more headcount or more labor in order to maintain that infrastructure. Okay. Now, with SD-WAN, it doesn't mean that you have to use, just one thing I want to clarify with SD-WAN, it doesn't mean with SD-WAN that you have to use the public internet, right? You can run SD-WAN over MPLS, right? technically you can run SD-WAN over anything, right? As long as you have that layer 3 connection or layer 3, you have a layer 3 connection from one branch to another branch, whether it's internet, MPLS, etc. As long as you have that, you can establish your secure tunnels, right? Another thing is a lot of vendors give you the option of not encrypting your traffic, right? And that would make sense in the case where you have you're running your SD-WAN over the internet and over MPLS, right? Because MPLS is, if you consider MPLS private, which is technically it is, right? Because you're not sharing that infrastructure with other tenants or other customers, right? Technically, right? You're not just sending traffic over the public internet. So if you consider that private, maybe you don't want to encrypt your traffic over MPLS, right? However, we do recommend that you would encrypt it anyways, right? But again, that's more of an organizational decision, right? Whether the organization considers MPLS private or not. Okay. So why would you use SD-WAN? Well, obviously, first is cost efficiency, right? Although the solution might cost a little bit more than traditional networking, but when you consider the ease of use, right, you can manage it with less headcount, right, with less labor, right? So you save a lot from the operational expenses standpoint, right? But also, if you think about not having to go to a solution like MPLS, that can also save you a lot of money. It's definitely cheaper than MPLS, right? It's very flexible, right? So it's easier to scale up, right? It's easier to scale an SD-WAN solution, right? So that's also a very important aspect of SD-WAN, right? Most of the things that you would do with SD-WAN, you can do with traditional networking, but it's very, very difficult to get the same level of granularity with traditional networking, without overcomplicating that solution, right? For example, there's different data plane, and I don't want to get too much into the low-level details, but there's different data plane policies and that you can push to each device. For example, you can ask a device to, let's say you have 2 tunnels from each site, and you can ask the device to send some traffic through tunnel 1, other traffic through tunnel 2, and you can say for the first tunnel, you want to set a rate limit, don't exceed this, and you can monitor the quality of each tunnel and only send voice traffic over tunnel 1. But if tunnel 1 suffers, let's say it falls below a specific threshold of a service level agreement, you can send it over tunnel 2. So there's a lot of cool things that you can do with SD-WAN, really useful things that can be done with traditional networking, but they're really difficult to maintain and manage with traditional networking. Okay, so simplified network complexity, right? Well, simplified. Well, it kind of the whole sentence doesn't make it. So yeah. So it reduces the network complexity, right? I think I'm kind of beating a dead horse with this point, right? Just saying everything that can be done with traditional network with SD-WAN can be done with traditional networking. It's just much simpler with SD-WAN. Yeah, that's SD-WAN. Do we want to take questions? Or
yeah, maybe we take 2 minutes of questions, 3 minutes of questions, 5 minutes of questions on SD-WAN before we get into transit gateways, which actually I'm sure everybody's going to be happy about. Get a little out of this pure networking stuff, a little more into the AWS stuff. But this networking concept is critical. And we're going to be using all kinds of WANs in cloud computing, SASE WANs, software-defined WANs, IPsec tunnels, private lines with IPsec tunnels. So let's get a few questions if we need.
So I see.
Will there be an SD-WAN lab? No, we're not going to make an SD-WAN lab. We've got a lot of routing labs, BGP labs, OSPF labs, VLAN tagging, VLAN trunking labs. and all those other things, but we didn't actually do an SD-WAN lab. We focused more on the bigger technologies that are going to be used in most cases, as well as the technologies that would enable you to learn what's going on under the hood. The key with SD-WAN is you basically click on a couple boxes and pretty much everything is done for you. So all the learning would be removed from the lab that we want you to learn, how packets are forwarded, etc. Were there any other questions here on SD-WAN? Or did Mo cover them today and I covered them with the YouTube video we made a couple days ago, which is quite possible. So before we get back to the content, we'll see if you have any other questions. If not, if you're enjoying something and you learned something, maybe give the video a like, maybe subscribe to the channel and hit the bell to be notified of new videos. For those of you that just joined us, we've got brand new AWS networking labs for you, and a lot of them, nearly 2 days full. They're being added each day until Sunday, and you can get them completely free by registering for them in the description or the chat box of this video. Orchestration. So yeah, let's talk about different kinds of orchestration. In normal networking, and my team can give you help as well, the orchestration's on the router. Inside of your network, you got routers, and they're running their interior gateway protocol that says, you know, how to go there. And it might say to me, to get to Benedict, go through Mo. And I know that this interface goes to Mo and that interface goes to Benedict. Here's the thing. The information is stored all on the routers. And the routers pass it to each other like a hot potato. I pass the packet to Mo, Mo passes it to Benjamin. If Mo doesn't have a link to Benjamin, drops the packet. So that orchestration, that control plane is on the devices themselves. What we're dealing with here is the orchestration is sort of like a pie in the sky. I like to view it as a satellite looking at what's going on in the network that's basically telling the devices how to forward their packet. So think of it that way. Is it every man and woman router device, you know, operating for themselves? Or is there some overarching policy that pushes configurations to things and tells people how to forward their traffic? That's the way I look at these orchestration. Either of you want to look at it differently? Or explain it differently?
Yeah, at the end of the day, the way I see it is Mike said, you know, you got different types of controllers. There's no one vendor, there's no that implement SD-WAN the same way. It's not like where each vendor, you know, agrees on uses an open source protocol like OSF or BGP. They don't agree with SD-WAN. There's no agreement on those two protocols, right? Some of those components might be common and they're reused. For example, IPsec is used for each SD-WAN solution. But really, each vendor does the orchestration part, the control part differently, right? So you can think of the orchestration as just a way to enroll a new device into your network. Just think of it that way, because you need a way to get that device enrolled into your controllers, right? So the orchestration is what that device that does that, right? So you can think of it that way as well.
Go to the next one. You were working with your AWS technical rep, and he said the AWS Advanced Networking exam is one of the hardest and something to be proud of passing. So here's a thought. It's a great exam, and you should be proud of passing any exam. The AWS Advanced Networking is about 500 pages of material. The CCIE that Mo has done is about 75,000 pages of material. Or the CCNP that Benedict done is about 10,000 pages to pass it, at least when Benedict did it, and there were 4 exams. So yes, it is a hard exam. It is a great exam. We love it, and that's why we're teaching it. But if we put it into context compared to other networking things, it's relatively basic. Now, AWS asks questions on exams in a very complicated, convoluted manner. So if you know networking, the biggest challenge of the exam will be trying to understand what they're actually asking in the questions, with all the acronyms, all the abbreviations, and questions that are 2 to 3 paragraphs long when they could be asked in about a sentence or so. Do you guys say that's fair experience? They make it hard?
Yep.
Your network has 120,000 smart devices connected to a control center. They're connected to SIM cards over third-party telecom providers. How to use SD-WAN in this case? Maxon, I don't think we know anything about what this case actually is. What devices need to talk to what devices? How are those devices connecting information, and what are they doing with those types of information? How is that information being aggregated? What are the performance needs of these things? What kind of broadcast or multicast traffic did they send, and how do we constrain this? I can tell you that we'd probably be able to talk to that customer that has this, maybe spend 8 hours asking questions, and then we can answer that question. But we don't know what we don't know with what you put in the chat box. And I'm aware that you're limited to basically 200 characters or so, but understand that's a full day's worth of questions to even understand part of what they're doing there. That's why there's so much that goes into architecting these things. And European VXLAN is overrated. There are limited use cases. Virtually everything today is going on layer 3 up to the edge. Not necessarily. You know, Tunde, I can tell you that I thought everything was going to go layer 3. And I literally tell you, in the early 2000s, I ripped out every ridiculous layer 2 bridge network you could possibly think of because I hated spanning tree. A year later, I was working with my team, and we were working on collaborating and creation of a virtual private LAN service. And we were creating layer 2 virtual private lines over IP networks, and we were back to using things. So I think the goal here is figuring out what the business goal is. I don't believe in any hype over any technology. There is no best technology. There is no great technology. There's a place for mainframes. There's a place for ISD and backups still in certain parts of the world. There's a place for private clouds. There's a place for public clouds. My perspective is the customer's needs drive everything. And I don't have a technology preference, but I'm an architect. I'm not an engineer. Either of you guys have a perspective on that?
Absolutely, absolutely. So yeah, I don't agree that VXLAN is over. I think it's a massive. So here's the thing, right? As it has a huge use case in data centers, right? Because in data there's more likely than not you need to stretch your layer 2, right? And if you're just using layer 2 end to end everywhere, it makes no sense because you're going to have oversubscription. You're going to have, because of spanning tree, right, loop prevention, you're going to have some links that are used, some links that are not used at all. So just the whole setup as a flat layer 2 can work for smaller data centers, but once you scale up, it doesn't work, right? Plus the VLAN IDs, you only get about 4,000 something VLANs. That's not enough, right? For, like, for example, Facebook, they can't work with just VLANs, right? They can't work with the traditional layer 2. That's where VXLAN makes sense, right? You look at it from, and again, VXLAN is a huge topic, right? But once you look at it from perspective of spine setup, what we call a class topology, right? Where you want to utilize all your links, so you layer 3 in your data center, but you still want to maintain layer 2 specific servers or specific virtual machines. So you run you get the best of both worlds, right? You're getting the layer, the benefits of the layer 3, but then you use VXLAN to tunnel layer 3 between those over that layer 3 infrastructure. So it's really useful. It's very, very useful for.
Yeah. Everything's got its uses.
Yeah.
I love these questions. They're really good thinking questions, which means y'all are awake. So give us a hashtag AWS Advanced Networking, and we will go back to the concept. I believe we're up to transit gateways. Is that right, Mo?
Yes.
Mo, you go wherever you have next. I think it's transit gateways.
Okay. Okay. So, transit gateways. Think of a transit gateway as a router. That's all it is. It's a router that allows you to connect multiple VPCs together. If you remember earlier today, Mike spoke about having a. Mike spoke about. That was not what I was trying to do. Give me 1 second. Bear with me. Okay. So earlier, Mike spoke about using VBC beers, right, or VBC beering, right, which was a method of connecting VBC-A to VBC-B, right, directly, having a direct connection between VBC-A and VBC-B, right, using AWS infrastructure instead of going over the public internet over a VPN tunnel and so on, right? So if you wanted that direct peering between VBC-A and VBC-B, you used VBC peering. But if you remember, we had the problem of n times n minus 1 divided by 2, right? Which basically says if you have 10 nodes, that means you need 10 multiplied by 9 divided by 2. We're talking about 45, right? So 45 VPC beers, which is, it can get out of hand very quickly, right? So what a transit gateway do for you, think of it as a way to have a hub and spoke setup. So if you allow me to add another page, and I'm not sure how, there you go. I'm trying to add a new slide. Okay, there you go. Okay. So if you think of it this way, you have VBC-A, VBC-B, VBC-C, okay? Now, if you want to establish a direct connection or peering between those VPCs with VBC peering, you would have one peering here, another peering here, and another peering here. You can't use VBC-B, so if this goes away, you can't use VBC-B to send traffic from VBC-A to VBC-C. It doesn't work that way. VBC peering is not transitive, it's non-transitive, right? So this can easily get out of hand, and you'll find yourself with hundreds and thousands of VBC peering connections, which is highly undesirable. So what a transit gateway would do for you is, we would take off these connections, and what we'll do is we'll add the transit gateway, which is technically a router, and that transit gateway will become your centralized router that can move traffic between your VPCs, right? Now, if you think about it now, if we added 2 more VPCs, all we need is just 2 more links, right? Instead of having to connect each one of these VPCs to each one of the other VPCs, right? So the transit gateway, number one, it acts as a centralized router that routes our traffic between all of our VPCs, right? A transit gateway can also run IPsec tunnels. So you can run IPsec tunnels with your, let's say, your on-premise, let's say this is the data center, right? You can establish an IPsec peering here, or a VPN tunnel, and now you have access to your on-premise. And the big benefit here is that each one of your VPCs will also have access to your on-premise data center, right? Think of this if you didn't have a transit gateway, right? You would need without a transit gateway, you would have needed a direct connect gateway in each one of these sites, and then you would have had to establish multiple IPsec tunnels to your data center. So you see how a transit gateway becomes very useful. So again, think of a transit gateway as a router, as a centralized router that can establish peerings between all your VPCs and data centers, right? You can also connect your transit gateway to a direct connect gateway, which is a private line, right? And have that connection to your on-premise. And now each one of your VPCs have access to that private line. So the benefits are big, right? Now with transit gateways, let's move on through the slides. So as we said, right, it reduces the number of required VPCs. So instead of needing an n times n minus 1 divided by 2, you would just need n minus 1, right? So if you have 5 nodes, you'll need five let's call them connections, we call them attachments, right? So it greatly reduces the number of required connections, right? If we go back to our slides, one second. Okay, if we go back to our slide, as you can see here, the topology to the left, this is a full mesh, right? The topology to the left, that's a full mesh, right? This is what you would typically do with VPC peering. The topology to the right, as you can see, this is more of a transit gateway setup, right? Where the transit gateway in the middle, everybody can talk to each other through the transit gateway. Okay. So what's the process of using a transit gateway? Well, you create your transit gateway, right? You create a transit gateway, and the transit gateway is a regionally available resource, meaning within the region, you have access to that transit gateway. So let's say you have an account, an AWS account, right? And you have multiple VPCs in that account, and let's say it's in US East 1 or North Virginia. You create that transit gateway, and then let's say then you can connect your 5 or 10 VPCs to that transit gateway, and now they all have access to each other, right? When you create a transit gateway, the way when you connect that transit gateway, that connection from the transit gateway to the different VPCs, it's called an attachment. Okay, so you create the transit gateway attachment, and when you create it, the transit gateway establishes a network interface, or ENI, inside your VPC. And then when you want to send traffic out through that transit gateway, you just point to that ENI, or that network interface that has been established, almost like transit gateway sets foot in each one of your VPCs, right? And you put your traffic through it. So it's transitive, right? Unlike the Direct Connect gateway by default, not Direct Connect gateway, apologies, we haven't spoke about Direct Connect yet. Unlike the virtual private gateways, which are non-transitive by default. Also, VPC peering, which is non-transitive. A transit gateway is transitive, meaning if you connect A and B through the transit gateway, A will be able to speak to B. Here's a visual representation of a transit gateway. Over here, you have accounts A, B, and C, right? Each one of them is in a different account, and the transit gateway is in a different account. This is very common, by the way. This is very common, and the reason why it's very common is the transit gateway, when you have a large organization and you have 20, 30, 100 VPCs, right? And each VPC is managed by a different team, let's say different application teams. You have your production VPCs, you have your production VPCs, you have your development and testing VPCs for different applications, right? You don't want one team's mistake affecting the other teams, right? So for example, if somebody runs a Terraform script in account A VPC, right? The worst case scenario is some resources in account A VPC will be deleted, right? If there was an error in that script, but it will not affect your transit gateway and it will not affect your other accounts, right? This is why a typical setup is you have different accounts, and so that one account's mistake wouldn't affect other accounts, right? And it can be a human error. I mean, aside from running an automation script, it could be somebody just going in manually. Maybe they just want to, a bad actor wants to delete your connections, right? So if they gain access to, let's say, account A VPC, they won't be able to affect the other VPC. So that's why we isolate, let's say, we isolate those different VPCs into different accounts, and we put the transit gateway with some other resources in a centralized account, right? Usually that's where you would put like your firewall, if you have a firewall, you can put your network resources, and so on and so forth. So with this scenario here, we have a transit gateway in one account, and then you have three different accounts. Each of the other accounts to the left, those are different VPCs, right? So now the VPCs, if you set it up that way, right? And the transit gateway is very flexible, by the way. If you set it up that way, you can have account A and B and C talk to each other. Those three VPCs talk to each other through the transit gateway. But you've also established a site-to-site VPN tunnel to your data center. And using this IPsec tunnel, the on-premises or the data center can speak to all your VPCs now. So as we move forward, you see the power of a transit gateway, right? Because it's transitive, because it's highly flexible, it can really open doors for a lot of different setups that wouldn't be available otherwise. Right. Yeah. So with a transit gateway, let's say that using your router, right, you have VPCs A, B, C, and D, right? Let's say VPC A and VPC B need to talk to each other, but VPC C and D also need to speak to each other, but A and B shouldn't be speaking to C and D, right? This is a very common setup where you have, let's say, two production VPCs and two development VPCs, and you want the development VPCs to talk to each other and the production VPCs to talk to each other, but you don't want production to have access to development and vice versa, right? Well, there's a couple of different scenarios here, right? Or a couple of different solutions here, right? Well, you can create two different transit gateways, right? And each transit gateway, create one transit gateway for development, another transit gateway for production. But a more common setup would be using that same transit gateway, but creating two separate routing tables inside that transit gateway. Create two separate routing tables. One routing table is for development and another routing table for production. And that way, development only talks to development, production only talks to production. Now, with this setup, right, this is a very common setup we have in our traditional networking, or let's call it on-premises networking, right? Typically, we call it VRFs, right? Virtual Routing and Forwarding instances. And all a VRF is that you almost split your router into multiple logical routers, right? Where one part of the router cannot speak to the other part of the router. And again, this is very common, right? And this is what we're doing with the transit gateway when you use multiple routing tables. Okay, so why would we use a transit gateway, right? What's the benefit? Why would we use it? Well, centralized management, right? Because now you're, instead of having 100 different tunnels, you have one place to establish, or 100 different VPC peerings, you have now one place to establish all your tunneling. Apologies, I keep saying tunneling, right? You have one place to manage all your attachments, right, or connections, right? It's much easier to manage, right? Also, you have enhanced security, right? Because of different functionalities like segmenting your routing tables. Also, there are very unique what's the best way to say it? There are very unique methods or that you can use, or they're very unique design patterns that you can use with a transit gateway that allow you to send all your traffic to a centralized firewall and then send the traffic back between different VPCs. So it allows for very unique inspection methods like an east-west inspection. Instead of just inspecting traffic that goes out to the internet and back, you can have a centralized firewall and have all the traffic, even between different VPCs, be inspected through that firewall before it returns. So it really opens up a lot of doors for a lot of different functionalities that can enhance security as well. Okay, and it can be cost effective, and it can actually reduce the cost of your infrastructure if done properly, right? But overall, it's more about adding more functionality and ease of use at the expense of adding a little bit of more cost. Because even a VPC peering can be very costly if not done right, right? And more likely than not, it's gonna cost you about the same, especially if you're sending traffic between different availability zones, which what we spoke about earlier. Okay. That's Transit Gateway. Do we want to take questions, or do we want to move forward to the next topic?
Address questions before we talk about IP multicast.
Okay.
So if you have some questions, type them in. I know there's a little delay. If you just joined us, make sure you download the labs. They're completely free. Links in the description of the video as well as the chat box. There's a lot of them. So, go download them, watch them, do them, that kind of thing. But just want to make sure you got it. Let's bring in the questions, Chris. Well, I'm trying to translate this. Can 3 VPCs be peered for communication? Absolutely. That is the point of VPC peering, but maybe I'm misinterpreting this question because it was hard to understand. Mo or Benedict, do either of you have a different interpretation of the question?
Yeah, I think that's what he means. I can't interpret it any other way. I think he sent the same thing again. Can the 3 VPC use VPC peering for connectivity? So if you have a full mesh where all VPCs are connected to each other, then yes. But if you have VPC A, B, and C, and you want A and C talk to each other through VPC B, then that doesn't work, because VPCs are not transitive.
Exactly. Not without Transit Gateway or Cloud Hub.
No. How do we implement security and maybe granular security controls with transit gateways, since they expose traffic data between multiple sites? Would it be better to implement security controls on a per site basis? That's a very, very, very good question. I love this question. So there is, as I just alluded to previously, I said that there are many different architectural patterns that are supported by a transit gateway, right? So one solution would be, just like you said, is to have, let's say, a firewall in each VPC so that your traffic is inspected before it leaves your network, right? Well, another method, or more practical, something that's more useful in my opinion, is it can be very cost effective too, is to have a centralized inspection VPC and have all your traffic sent to that centralized inspection VPC and have it inspected before it exits out to the internet, or even between two different VPCs. You send your traffic to that centralized inspection VPC where it hosts your firewalls, and then have it sent back. So both east-west or north-south. So that's a very extensive topic, right? I'm sure Mike will cover it at some point, but definitely not within this program, because it's really extensive. It's not even something that will be covered that extensively in this exam.
Not at all. But we do have other security training coming up.
It is not, no. So a virtual private gateway, if you think about it, does not allow you to connect one VPC to another VPC directly, right? It's more to connect to private lines and VPN tunnels. So that's a virtual private gateway. But a transit gateway, so think of virtual private gateway as an edge router that allows for VPN tunnels and private lines. But a transit gateway is a router that also does VPN tunnels, but it also allows you to connect multiple VPCs to each other using AWS internal infrastructure, right? So you don't have to go out through the internet, encrypt your traffic, and none of that. So think of it two different tools that have different use cases.
I like to think of it, King, a transit gateway as a router that just doesn't have quite as many features as you'd find on a Cisco router and Juniper router that you would use for BGP. So BGP peer to the transit gateway, and you route. Kind of like we've done for the last 20 some years, 30 years with regular routers. That's all it really is.
So why use a well, think of it, why we use a transit gateway is it's not transit gateway versus virtual gateway. It is transit gateway versus VPC peering, really.
Mm-hmm.
That's the main thing, right? Because with a VPC peering, you would need full mesh. So all your VPCs need to be connected to each other. But with a transit gateway, it's more of a hub and spoke, right? Everybody can talk through that transit gateway, right? Now there is an overlap of the things that transit gateway does and a virtual private gateway does, but they're not the same thing. So I would say because a virtual gateway is not transitive.
And Sunday, if you want to look up and get more information, look up a BGP route reflector, because the BGP route reflector 30 years ago is effectively the transit gateway of today. And iBGP, and if you read the BGP RFCs, they're completely free on the IETF webpage, which is why I'm using it. They talk about fully meshing our iBGP peers. And now you've got an organization that's got 3,000 routers, and how do they create a full mesh environment of 3,000 routers? So they came up with a couple ways to be able to chop down the networks to make it scale better. One was something called a confederation, which was chop basically your environment or your autonomous system into multiple smaller ones. And the other was a route reflector, which is peer to the route reflector. It breaks the rules of non-transitive routing, and hence Cloud Hub, transit gateway, same kind of thing. Sometimes if you know where it's coming from, it helps you know where it's going.
Yeah. Do I see any cloud technology that can replace transit gateways? Not really. I think the use of a transit gateway is very important. To replace it, that means AWS has to replace it, really, right?
Yeah.
Because if AWS decided to create something else, because the real benefit of transit gateway is that it has its hooks deeper into the AWS infrastructure than you would, right? For you would need to create VPN tunnels over the public internet. No, AWS uses the internal infrastructure. So it's really hard to replace unless AWS decides to create a new solution. So I think one solution is not really a replacement, but more of an addition, which is AWS's SD-WAN solution, right? Which is called, I believe, Transit Gateway Connect. And with Transit Gateway Connect, it still uses transit gateways, but it using the same transit gateways they're using, it adds the same management plane on top of that. It allows you to do different segmentations. It's literally, it literally is the same thing that you can do with a transit gateway. They only simplify it for you, right? So I would say if there would be something that to replace transit gateways alone, it would probably be Transit Gateway Connect. But it's hard to replace it unless they want to replace it.
And it's hard to replace it because it's not like they just want to give you a Cisco router that's connected to everything and say, here, configure your Cisco router or your Juniper router. That is sort of their router. These are good questions.
Okay.
We may pop a poll into the chat box for you guys. I want you to look at something we're thinking about after some of the questions you've asked us. And some people have asked about slides, and our slides are only to organize our own thoughts. Mo may have fancy slides. I may have 3 words at a time on a piece of paper because that's the way I give a presentation. But there's a potential we'll write a book on it and give the book away free like we typically do, like we've done for the AWS Solutions Architect Associate. So we'll think about it if there's enough desire and potentially enough resources. So, we'll ask you a poll on that. And then we can bring in a couple more questions and then we can get back to the content.
One thing I want to say before, Mike, I just want to, I said Transit Gateway Connect and this AWS Cloud WAN. That's their SD-WAN.
Yeah, that is the Cloud WAN solution. So from Kevin, if a client doesn't have a CCI, would micro-segmentation be too complicated for companies? Kevin, I want to completely segregate competency versus CCIEs. I know many people that have not done a CCIE that are better than CCIEs. You give me Benedict, who's a CCNP, I could find him anywhere, and any company in the entire world would be more than likely to have Benedict. He's that great of a network architect. And prior to that, he also was a network engineer. He's that good there too. So Benedict could do this stuff in his sleep. I'm a CCIE, I could do it. I know other people. I worked with this guy, Ted. Ted never got a IT certification his entire life. He didn't finish high school, but he was one of the best network engineers I ever met, and he could do all this stuff. So the key is, yes, you're going to need people to micro-segment that really understand networking. Alternatively, you're going to need a simpler solution like an aviatrix. But there's an incredible number of people that know a whole lot, regardless of their certification.
Is a transit gateway, that's a good question. Is a transit gateway a global or a regional resource? If regional, can we create peering between 2 transit gateways in case we have VPCs in 2 separate regions? Yes, it's regional. It's highly available. It's regional. So if you wanted to connect multiple VPCs within the same region, you would use 1 transit gateway. But once you want to, if you have other VPCs in, let's say, in a different region, then you would need to create a transit gateway over there as well, and then peer those 2 transit gateways, which we call a peering connection between 2 transit gateways.
All right, so we're going to get back to the content. Mo is going to talk about one of my favorite concepts, which is IP multicast routing, which is something that I've done all over the world. So Mo is going to get geeky into the AWS side of multicast routing, which is very important. If any other multicast routing questions come back after that, maybe with regards to PIM or IGMP or slightly different stuff, we'll tackle them too, and we will have fun with it. So Mo, thank you so much for sharing your expertise, and let's go back to you.
Awesome. Okay. Yeah, AWS multicast. Don't be scared. Don't be fooled. AWS's implementation of multicast is very simple. I think it's smart, but it's very basic, right? As compared to what Mike used to do back in the day at a larger scale, that you can't even compare that, honestly, because the simplicity of the cloud, right? there comes a lot of limitations, right? And even multicast is set up in a very, very basic and simple, limited way, right? But it does it does the job for the most part. So as we know, there are 3 types of IP traffic, right? Unless I'm forgetting one. But last time I recall, there's unicast, broadcast, and multicast, right? So unicast is when you have router A, or let's forget about, let's say you have PC, another PC here. Let's say you have a switch here. So it's a layer 3, right? So 1, 2, and 3, right? Unicast is traffic that's going from 1 to 1, okay? A broadcast is you just flooding your traffic and you want everybody to listen to that traffic, right? So you send a broadcast, that means you want it to be received by both. Okay? A multicast is something, you can say something in between. A multicast is you send traffic, it's one to many, right? If you remember, we said unicast is 1 to 1, right? A broadcast is 1 to all. A unicast is 1 to many, which means that you send the traffic, receive it. So you have to subscribe for it, right? So you have your network like this, right? Let's say we have another host, let's say 4. Let's say only 2 and 4 need to listen, or let's say only 2 and 3 need to listen to this multicast traffic. 2 and 3 need to subscribe in order to receive that traffic. And this host sends that multicast traffic, then the switch will know to send that traffic here and here. Now, the switch is able to do that because there's a protocol called IGMB, or Internet Group Management Protocol, right? And what IGMB is a protocol for devices within layer 2, within a broadcast domain, for routers to be able to request multicast traffic, subscribe, or join a specific multicast group, right? And so multicast has a specific IP range, right? I don't remember off the top of my head, but I think it's 224.0.0.0/6. Information that you don't need to memorize because it's readily available. Okay, so it's 224.0.0.0 all the way to 239.255.255.255. So this is the range I use for multicast, right? For example, if there are some IPs on this range that are reserved, right? For example, there's a multicast range that's called the all routers range, which is the 224.0.0.1, and then you have the all hosts, which is 224.0.0.2. So these are reserved, right? Typically what we use for private use, we use the range 239.0.0.1 /16. So this is typically the range that we would use for multicast for our applications, but it's not set on stone. We don't have to use only this range, right? So again, going back to IGMP, IGMP is a protocol that you use, or the clients use, or the host, in order to subscribe, right? Because when you send traffic, there's a source or a sender, right? You have a multicast sender, okay? And then you have a receivers, right? In this case, our receivers are host 2 and 3, right? This is where host 2 and 3 needs to send an IGMB join to say, I need to join this group, right? So they send an IGMB join, right? Notify the sender that they need to receive multicast traffic, right? Now the switch typically switches would run something called IGMB snooping. And some of you might already understand what this protocol does just based on the name. IGMB snooping does is that the switch will listen for the multicast traffic, even though it's not intended for the switch. The switch can listen, and based on that information, it will know who wants to join a specific multicast group, who wants to leave a specific multicast group. So instead of the switch just broadcasting the multicast traffic everywhere, it will more intelligently send that multicast traffic to the right people, pretty much, right? And so IGMB snooping, because without IGMB snooping, the router, the switch will treat multicast as if it's broadcast. It will just broadcast it everywhere. And that's why IGMB snooping is very important, right? And it does that as again, I don't want to go too much into details because it really can get granular, but think of it this way, right? Because the switch, it's a layer 2, so it only listens to layer 2, right? So how does it know the actual group, the multicast group? It knows because at the MAC address layer, right, when you send the multicast traffic, each multicast packet is mapped, each IP, multicast IP, let's say 239.0.0.1, can be mapped to a layer 2 MAC address, right? So there's a layer 2 multicast MAC address range too, right? So when you activate the IGMB snooping, the switch will listen for that range and it will know where to send that traffic based on the IGMB snooping protocol. It will know the senders and the sources and the receivers. Okay, so the source is called the sender or source, which is here, the sender. The receivers are sometimes called subscribers because they have to subscribe for that group. Okay. Okay. So what's the benefit of multicast routing? Well, it's very, very useful for use cases like video streaming, financial trading platforms, in cases where you want to send you're sending traffic from one sender to multiple receivers, and you want to send that traffic in the most efficient way possible, right? And if you think about it, the most efficient way possible to do that is to actually send your traffic instead of having to replicate it multiple times. Because over here, if you think about it, right, let's say I have a financial trading platform, right, and I receive real-time data, right, price changes and stock changes, so on and so forth, right? If I have to replicate that traffic and send it individually to 2 and 4 and to 3, that's not very efficient, right? Because the sender has to replicate that traffic multiple times before it sends it. But if I send it as a multicast, right, then it will go directly only to, number one, I'll only send it once, right? But that traffic will be sent only to the intended receivers, right? Obviously, there's a third solution, which is broadcast, but that's very inefficient, right? But having to send traffic to 100 devices, but you have millions of devices, right? In that case, broadcast is not efficient, and that defeats the whole purpose of the efficiency, right? So that's why multicast, think of it as something between unicast and multicast, right? Unicast and broadcast. Okay. Chris, can you share my screen? Yeah, I just looked back at my screen, so I'm not sure if you saw me when I was drawing this topology. I hope you did. But moving forward,
Yes, that was there.
so
They saw that.
Okay, perfect. All right, because I got lost for a second trying to find my screen. Okay. So another use case of multicast is IPTV, right? IPTV is basically IP, or getting TV broadcasts over IP, right? And you have different subscribers, and those subscribers would use, will need to watch TV in real time, right? So it makes more sense to just broadcast it only to the desired listeners, right? So it's almost like you have a radio and you tune into your channel, right? And you would only listen to that channel if you need to, right? So you subscribe for it, kind of. But the difference is with broadcasts, like radio broadcasts, that traffic is sent anyway, right? It's broadcasted anyway. And then you choose to listen to it or not. But with this, is even more efficient because the traffic is sent to you and delivered to you in an efficient manner, right? One to many, only if you want to listen to it, only if you subscribe to it. So you actually have to subscribe to it. So we talked about financial trading platforms, right? IBTV. It's very useful for real-time data, right? As you're sending, instead of replicating data multiple times, you want to send it from point A to point B the fastest way possible, right? I see some comments are giving very good examples on what good use cases for multicast, right? Live score updates, example John said for sports, right? Sina or William said multicast is like TV, right? Just sync the channel, right? It is like TV, except for with TV, that's a radio signal that's broadcasted everywhere, almost like a broadcast, right? But with multicast, you actually have to subscribe for it in order to receive it. So how does AWS implement? So before I start this point, I want to point out one other thing, right? In traditional networking, right, we spoke about only of in this example, this is traditional networking. We spoke about only having to send traffic over a broadcast domain or over a layer 2 domain. In reality, you have multiple networks and you have routers, and those different routers connect to each other, right? And you might have a router that's in a different part of the world that connects to your data center through an IPsec tunnel, and you want to send multicast traffic, or let's say over a private line, and you want to send that traffic to that remote site, right? In those scenarios, IGMB alone doesn't cut it, right? You're going to need something else because now you introduced routing into the issue and it complicates things, right? This is where we would use protocols like prefix independent multicast or PIM, and it really gets really granular. That's a huge topic on its own. It's outside of the scope of AWS, and it's not used in AWS cloud to begin with. But just keep in mind the comparison here. When we compare traditional networking or on-premises networking, we're comparing having one layer 2 domain, and then that layer 2 domain, just multicast within that layer 2 domain, right? It's compared to that. It's not compared to having to use like a multicast routing protocol where it really gets gets more complex. Okay, so how does AWS implement multicasts? Well, with AWS, they use the transit gateway in order to implement multicast, right? So if you remember from the previous topic on transit gateways, we said that a transit gateway establishes an attachment in each one of your VPCs, right? And if you remember, I said when a transit gateway attaches to a VPC, it sets its foot on that VPC. So it creates an ENI or elastic network interface in each one of your VPCs, right? Now, with that in place, if you have, let's say, 10 VPCs and each VPC has a transit gateway attachment, it has an ENI, that means, and because transit gateways are an AWS resource, right? So they're more integrated with your AWS infrastructure, right? There's an opportunity here to use the transit gateway for multicast. And the way that is done is not really a true multicast, but it's more of what we would like to call traditional networking. I think Mike will agree with me when I say we call it more of a pseudo multicast. So it's not true multicast, more of a pseudo multicast, meaning it's really more of a replication of your multicast traffic. But the benefit here is with the transit gateway, your end host or your server or machine does not handle the replicating that multicast traffic. Is the transit gateway that does that for you, right? So as far as you're concerned, it is multicast, right? And the packet is multicast, but the transit gateway replicates that traffic into your receivers, the intended receivers. I'm a visual person, so I'm gonna go to my diagram, kind of explain from there. Okay. So as you can see here in this diagram, I have VPC A, VPC B, and VPC C. Okay. So between those three VPCs, your transit gateway established an attachment to each one. Now it has an ENI in each one of those VPCs. Let's say in this example, you want EC21 and 2, let's call them N3. You want those three to be able to talk to each other, right? Use a multicast. Let's say 2 is the sender. This guy is the sender or the source, right? And 1 and 2 are the receivers, right? Or subscribers. Okay. Now, let's say that the group that we're using is 239.0.0.1. Okay. That's the multicast group, right? The sender first, needs to, the transit gateway needs to know where the sender is, right? And there's two methods we can do this. We'll start with the first one, which is statically. We can statically, on the transit gateway, you enable multicast, number one, you enable multicast, right? And then you create what we call a multicast domain, right? And each one of your subnets can only be part of one multicast domain. Okay. Think of the multicast domain as, well, it will make sense as I explain it, right? But the multicast domain is the domain that is shared between different VPCs or different ENIs inside those VPCs, right? So in order for the sender, which is 2, to be able to send multicast traffic to 1 and 3, they all have to be in the same domain, right? And then once I create that domain, it's part of the transit gateway. I need to say, okay, I'm going to attach this subnet, and this subnet, those 3 VPCs, those subnets inside those 3 VPCs, I need to attach them to this domain, to this multicast domain, okay? And then I need to create the group, which is 239.0.0.1. I need to create that and say 239.0.0.1. And for 239.0.0.1, the the instance number 2 is going to be the sender, and those 2 are going to be the receivers, right? And then of course your application itself inside this machine needs to accept or needs to send multicast traffic, right? And then 1 and 3 will be able to receive that traffic. So when we send that traffic from 2 to the transit gateway, the transit gateway is doing true multicast. It's still receiving, but what it's doing is it takes that multicast packet and then it will replicate it to the instance 1 and to instance. That's why I said it's more of a pseudo multicast, not a true multicast from AWS perspective, right? But the benefit here, your hosts, which is host 2 here, your instance 2 here, didn't have to replicate that traffic multiple times. You only had to send, right? So you still get the same benefit. So this is more of a static registration. This is what we call static registration, okay? The other type of registration is dynamic, and it uses IGMB, just like we talked about IGMB previously, right? For when we gave an example for traditional network or on premises. With that example, we talked about IGMB, right? Well, we were talking about IGMB version 2 in that example, right? And IGMB, just as we said, your host can register or join a multicast group, right? And then your transit gateway can listen to that register message, almost like a switch using IGMB snooping, and it will recognize and record that the specific host needs to listen for multicast, right? And then the sender, in the same way, the sender needs to send the multicast traffic. Now, there's only one thing different here, right? The sender, if the sender is both a sender and a receiver, which means you need to send and receive multicast traffic, then you can use IGMB version 2 and the transit gateway will register you as a sender and a receiver. But if you're only a sender, which is most typical case, right, where a server is a sender and then you have multiple receivers, that if you're only a sender and not a receiver, then you still have to statically register that sender. One other thing is, if you want to be a sender, you have to use an EC2 instance that is a Nitro instance, right? So it has to be a Nitro. It needs to use a Nitro network interface card. It can't be a regular EC2 instance. It has to be a Nitro instance. It can't be standard, right? Because there's standard, there's Nitro instance. Okay. If we go back to our slides. Chris, if you think, thank you. Right. So dynamic registration, right? The transit gateway will send IGMB queries, right? The host will send an IGMB join, right? They will ask to join, and then you will register it as a receiver. For the sender, you will have to register statically. Now, one thing I want to point out, by default, all, well, not all, but AWS Linux instances are set up by default to use IGMB version 3. Because IGMB is set up, so multicast or IGMB is set up at the kernel level. It's not at the operating system level, as in, I mean, it's not on your software itself, right? It's not on your application, right? The actual operating system takes care of it, is what I'm trying to say, right? The operating system takes care of it, not the multicast application that you have on top of that Linux machine, right? So you need to change it to IGMB version 2 because that's the version that AWS supports. It doesn't support IGMB version 3. It supports IGMB version 2. So make sure to keep that in mind. If you want to be a sender, you have to be a Nitro instance. And in order to use IGMB to dynamically register your sources, you need to make sure that you set up your instance to use IGMB version 2 instead of IGMB version 3. IGMB version 3. I'm pretty sure I'm forgetting one other thing, a very important point. Yes, okay. The third thing is your receivers. You need to make sure that the receivers disable the option for source destination IP check. And what that option does is by default, there's a protection mechanism where an EC2 instance, if it receives a packet with a destination that is not its source IP, it will discard it by default. So if I have an instance and my IP is 1111, but I receive a multicast packet that has a 239, by default, that instance will say, well, 239 is not my IP, so I'll just discard this packet, right? So typically, if you have an instance and you set up that instance as a firewall, for example, right? It's very typical for that firewall to not, it's very typical for that firewall to forward traffic that is not intended to it, right? Because traffic goes through that firewall. So typically in a firewall, you would disable that option. It's the same thing for multicast. As a sender or a receiver, you need to make sure that that's disabled. Only that with a Nitro instance, you don't need to disable it. It's not used by default. But so that means technically the sender, since it's Nitro, you don't really care about disabling that option. You can disable it. But for receivers, you have to disable it if you're not using a Nitro instance, which more likely than not, you're not using Nitro instances. One other thing I want to bring up here, which is if you're using access lists, if you're using security groups, you need to make sure to add those policy, the security group policies and the access list entries to allow for the multicast traffic, right? And the first traffic that you need to allow is a IGMB. So this is IGMB version 2, right? With a source of 0000/32. Why 000/32? Well, that's the IP that the transit gateway uses when it queries your instance, right? When it sends IGMB queries, when it asks you what groups do you want to join, it will ask you with a source IP of 0000/32, right? So this is the first part that you want to enable. Notice that they don't put the destination. We know that access list has a source and a destination, right? And notice this is straight from the AWS documentation, by the way. Notice that they don't have the destination here. But in reality, when you create, I think this is incomplete information, honestly. But in reality, when you create this, there's usually a destination part of the access list, right? So you need to make sure to either put your IP address over here as a destination, or just leave it open. Actually, in fact, because this is IGMB and you're querying, right? You want to make sure that it's using the IGMB query, which I forgot what's the destination IP, which is well, it's going to use 224.0.0.1. It's going to use 224.0.0.1. If you remember, we talked about the all host IP address and all routers IP address, 224.0.0.1 and 224.0.0.2, right? So 0.1 is all hosts, right? So you need to make sure that the destination here is 224.0.0.1, okay? And then you need to allow the actual multicast traffic itself, right? So in this example, you're using UDP, you're sending UDP traffic, or you're receiving UDP traffic, right? And so when you receive UDP traffic, right, you want, number one, the IP address of the, you want to allow traffic coming from the IP address of the sender or the source, and you want that traffic distant to the destination multicast IP. So in our example, we said 239.0.0.1, right? And now, of course, outbound is the exact opposite, right? Well, with outbound, well, not the exact opposite. It's the exact opposite for UDP, right? Because the destination becomes the multicast group IP, and this is more of for the sender, right? But also you need to allow to send IGMB join or IGMB leave, right? So you need to allow those IGMB traffic as well for the source and destination. So we do have a demonstration for this exact topic, right? And I did go through how to set this up, how to set up the security groups. I haven't set up the access list. I kept the access list open for that example just for brevity reasons. But it's the exact same thing, right? We talked about access lists. Notice that security groups are pretty much identical, almost identical. IGMB is IP protocol 2. So this is the same thing. If you notice, everything else is the same. Okay. So why should you use multicast routing, right? Well, number one, efficient resource utilization, which means you're utilizing your resources better, right? You don't have to replicate that same packet again and again and again, right? Your host will only send that multicast traffic once. It will only be received by the intended users without having to replicating that traffic multiple times, right? Let the transit gateway take care of that. And then enhance the application performance because you don't have to replicate that traffic multiple times, right? This is perfect for real-time traffic because you only send it once and it will be received by all the intended receivers. So that's IP multicast. If you have any questions, more than happy to answer.
Let's come back. Let's ask some questions. And I want to do one thing before we get to the questions. I want to talk about why the stream we're dealing with today is unicast versus multicast. So I want to just give you guys a little bit of an example of how multicast works outside of the cloud. This is a cloud thing. Mo gave you a very good, very detailed cloud. But I'm going to give you a perspective of how it would work in the traditional environment. I think this may help clarify a few things. So right now, this is a traditional local area network. Right now, I've configured it for nothing other than traditional unicast routing. Let's say your users at the bottom underneath R2 want to access information. In a unicast environment, like we're actually in right now on YouTube, the users would basically go and ask for the information, and the source would send the information through the network to the users. So if we've got a host on the left and we're all watching YouTube, we're all connected to the unicast address at YouTube, and then YouTube will literally replicate it for host 1, it will replicate it for host 2, and it will replicate it for host 3. Now, YouTube uses the entire internet. The entire internet does not have IP multicast routing enabled, and that's the reason why you'll see this for YouTube. Now, let's take this off of the public internet. Let's turn it into our private network. And what we would have to do is we would have to enable IP multicast routing on each router, and we'd have to enable a multicast routing protocol, typically PIM. Protocol independent multicast would be used, and specifically sparse mode. But for right now, what's the point of this? We would enable this on router 2. We would enable it on router, well, actually, this should be router 3. It might help if I could count. We'd enable it on router 2. We would enable it on router 1. And we would also enable it, and it would be enabled on all interfaces on router 1. So now what would happen is we'd have the source. What was that big show that was on Netflix that everybody liked? Was it Black Mirror? So basically you'd have a source, say Black Mirror, that would post itself if it was a TV show, if it was live broadcast, inside of your corporate, maybe your stock things, maybe your IPTV and your private cable company. The source would start to broadcast and it would instantly register with router 1. Router 1 in its multicast routing table would see that it has the multicast group 239.1.2.3, which was coming from the source IP address of 172.16.1.1. Now, if we owned the network and we enabled IP multicast, the host 1 would like to join. It would send an IGMP join group message indicating that it wants the presence of 239.1.2.3. It would immediately hit router 3. Router 3 would say, I'm going to open the port on my Ethernet to, 239.1.2.3. It would then send this request to router 2. Router 2 would then open what it's called its outgoing interface towards router 3. it would then go to router 1, and router 1 has the traffic on it. It would immediately send the information out its outgoing interface. So now host 1, and I'll enable them as host 1, is receiving the IP multicast. Now someone else wants to receive it. Guess what they do? They go to router 3. They say, send an IGMP join group message to router 3. Router 3 already has the IP multicast. So it just adds that port, or if it's a layer 3 switch, and starts sending it to host 2. Now host 3 wants to watch that same live show Black Mirror on Netflix, but it's live, not on demand. It sends an IGMP join group request. Router 3 sends it back. But in order for this to happen, we have to be on an IP-enabled network, a network which would support a network multicast routing protocol, such as PIM or DVMRP, and it would also have to support and enable us to let the routers actually replicate our network traffic. So that's traditional multicast routing. That's why what we're doing on YouTube today is actually Unicast, even though it would be a whole lot more efficient if the entire internet was IP multicast enabled. And imagine how many less servers YouTube would actually need. When everybody wanted to watch the same thing, they could subscribe at the same time. Just think about how efficient that would actually be. So hopefully answered that question on why some of it was unicast versus multicast. Let's get into some questions. No questions for real? On IP multicast? On any of that hardcore, heavy duty stuff that Mo went through? You all awake? And yes,
Okay.
William, we have to enable multicast on every single router along the way and on their list to make it happen.
Yeah, pretty much.
That's why what we're dealing with here is unicast, even though multicast would be more efficient. But now you've got cable TV, right? Or fiber to the home. Now the service provider that gives you your TV has control of the network, so they can enable the IP multicast routing directly in there. And what you typically have is your video plugs into an encoder. It multicasts it on the network. The routers and switches do their thing, and everybody's all kinds of happy.
Yeah,
So the next question so yes, you would need to enable multicast hop by hop in order to take benefit of the protocol. So now, Tenacious Bob actually brought in an interesting question. So if he's getting me right, yes, we can't multicast on the public internet because you don't have control over the routers on the internet. And you can't enable IP multicast routing on every different internet service provider's router that exists to get it here, because your traffic goes through many internet service providers or autonomous systems that you don't own. But if it was your own, yeah, you'd be able to control it and you'd be able to do it. Now, if we had to multicast through the public internet, or if we had to do heavy duty multicast across AWS into Azure, more than the IGMP that Mo talked about, Mo gave you the perfect technology to fix this. We could create a GRE tunnel in our data center across the internet, and we could push our IP multicast across the internet by tunneling it through the internet. And now you know why Mo was talking about these complicated overlay networks and this GRE tunneling, and we networking people love tunneling because it enables us to take stuff and then put it inside of something else. And that way, when we don't have control of the network, we can still give ourselves control.
So I thought I would let you know, Mike, that we have had 79 people vote in the poll for the exam guide possibly being made. 14% said that as long as there are cat pictures. So, there you go.
Anybody wants cat pictures? I got a cat named Cindy. She's absolutely beautiful. I got cat photos for days. It's funny. I have 3 pictures of myself and my wife on my phone and about 1,500 pictures of my cat. But I guess any cat owner knows that. If you have a cat, give me a hashtag cat. If you got a dog, it'd be a hashtag dog. But in any case, any other questions before we go to talk about some more technical content? Okay, I am going to get into access control lists. So bear with me, Chris. I'll come back on screen. Okay, so I'm back, and hopefully my 3 internet connections hold out for the rest of the day. You have no idea what can go wrong will go wrong. I love dogs, cats, anything, you name it. I love anything with fur, feathers, you name it, I love it. So let's talk about packet filtering. You know, we have to add security into our systems, and there's lots of tools. You know, at the edge of our networks, we're typically going to use our next generation firewalls. Inside of our networks, we may not want certain traffic to talk to certain other traffic. Like maybe we don't want subnet A to talk to something in subnet B. So what do? Well, we've actually been creating access control lists on routers. If you did a CCNA, you may have done your standard access list and your extended access list. Well, in AWS, they call it a network access list. And honestly, the term that AWS gave it, network access list, is really better. Because, you know, to us networking people, an access list is just an access list on the network, a packet filter. But in the Unix world and the Windows world, they have access control lists which determine how you would access certain resources and permissions. So they also call them access lists. So for clarity, let's call it a network access list. And it's just the ability for you to be able to tell something that it can talk to something or can't talk to something. So access lists are a bit like firewall. By default, they block everything, which means if you create an access list and you don't permit something, I promise you just broke everything. I promise you. And you can break a lot of stuff really fast with an access list, but you can also add in a lot of security. So an access list can enable you to allow or disallow traffic based upon something. Now, what is that something? Typically source address and destination address, protocol and port numbers. So source address, 192.168, talking to 2222. That is the source address and the destination address. Protocol, TCP or UDP. And port number. Are we connecting to port 443 because it's SSL? Are we connecting to port 80 because it's unencrypted web traffic? Hopefully we're not, but you get the point. So an access list enables us to create a policy to protect a subnet from traffic. You may see that on a question, protect a subnet from traffic. So let's talk about something you don't want to do. And believe me, anybody that's ever been a network engineer has done this before. So access control lists work in order, meaning they look at the rule, they take an action upon the rule, and then they do move on to the next rule. So let's say we have traffic coming into an access list, and the rule is deny everything. And then after we say deny everything, we say, oh, wait, allow you to connect to the web server. But we already threw out the traffic. It's not going to get to the traffic. So we have to have our permits, typically speaking, before we have our design. Now, the next thing I want to talk about is stateful versus stateless. Access control lists are stateless. The stateful versus stateless is critical. Here's the difference. A firewall, all of them for the most part are stateful. My iPhone just right now became a firewall so I can alleviate state. Let's say I am here and I want to go to a website, www.gocloudcareers.com. And I'm sitting here and I am having a stateful access list because it exists on a firewall versus a non-stateful access list that exists on AWS. I initiate my traffic. I'm behind the firewall. My finger is the traffic. I type www.gocloudcareers.com in my browser. My traffic goes out through the firewall. My traffic leaves the firewall. The firewall says, that's Mike Gibbs traffic. Go into gocloudcareers.com. My traffic hits the GoCloudCareers web server. It then comes back, and the firewall says that is GoCloudCareers traffic designated for Mike Gibbs because Mike Gibbs previously requested the traffic. Allow it in. So it's keeping track of my traffic going out and allowing my return traffic. The keeping track of it is what's called stateful. Now, by comparison, we've got Hal the hacker. And if anybody has the name Hal, I don't mean anything. I was just trying to alliterate here. But we've got Hal the hacker that tries to come into my website. He or she is immediately blocked. Why is Hal the hacker blocked? Because they're not permitted by the firewall, and they didn't initiate the connection from the inside, and the firewall didn't have state on the outside. So now that you know what is stateful, we keep track of it. Stateless is we don't. Now, if the firewall didn't have access of didn't keep state to know that I initiated traffic to go cloud careers, it would block it. Well, access control lists on routers, network access control lists in AWS are stateless, so they don't keep track, which means you'll have to apply them both inbound and outbound if you want the return traffic to come back. No big deal. Now, I mentioned they're in order. So I mentioned don't deny all traffic and then permit something. Do this instead. Let's say I only want to allow unencrypted web traffic for whatever reason to the system. I'm going to allow port 80 traffic from any source in, and I'm going to allow the return traffic from port 80 traffic out. By doing so, nope, I don't have any denies because the deny is in place. Let me give you some general guidelines. When you create these rules, they are processed in order. So you might think rule 1, rule 2, rule 3, rule 4, rule 5. You might want to do that and count that in chronological order. I beg you, please don't do this, because what's going to happen is you're going to think you need a rule now, and then you're going to need another rule now, and then you're going to need another rule. And if you have your things processed in order, you're going to get yourself in trouble. So maybe rule 1, maybe rule 10, maybe rule 20, maybe rule 30, or maybe, rule 10, 1, 50, 100, but give yourself some opportunities to create new rules on demand and remove them. That's all we go. Access control list, simple, stateless packet filter. And you use access control list to protect a subnet. The whole point of the access control list is simply to keep traffic out of the subnet. So now we're going to talk about a security group. What's a security group? Well, a security group is very simply a host-based firewall, if you want to call it that. So you've got your server. You could put a host-based firewall on it, and I recommend you do. From an enterprise-grade organization, put a host-based firewall on it. And what a host-based firewall does is it protects the server. Well, AWS offers a concept that's very similar to a host-based firewall that you can use to protect your AWS infrastructure. You want to protect your load balancer? Put a security group on the load balancer. Don't believe me, it's not enough. You're going to want to use real other security too, but it gives you something to protect the load balancer. Very similar to a host-based firewall. Now, does this mean we shouldn't use the security group and then a host-based firewall on our servers? No, we should use both because we want defense in depth. The more layers you have to an onion when it comes to a security, the more likely you are to survive an attack. But security group protects a service or a server, and network access control list protects a subnet. So keep that in the back of your mind. Now, because a security group is like a firewall, it is stateful, which means if you allow traffic into the server, for example, it's going to naturally allow the traffic to go back to the source because the security group is stateful, just like a stateful firewall. Now, when it comes to the security group, you only need to create inbound rules. Permit this. Why? It's a firewall. Permit what you want in. Everything else is going to be magically, automatically denied. Because firewalls are security devices. So wouldn't you think if your door was a security device, it would remain locked, and then you'd give the key to the people you want in? That's all we're talking about security groups and access control lists and network access control lists. They're locked until proven otherwise. So while I showed you that we use the access control list for the subnet, we use the security groups protect the host. There you go. Very simple. You see, the instance, which is basically just a virtual machine, is protected by the security group. Now, in real life, I'm going to do a lot more to that server to make it secure. We're going to disable the unnecessary services on this thing, close unwanted ports down, patch it, add some endpoint protection, maybe some anti-malware, maybe an enterprise-grade host-based IPS system and a firewall. But these are the cloud-native security tools that are available for you. Now, let's talk a little bit about VPC flow logs. So what's a VPC flow log? So for those of you that understand networking and been in networking for a while, maybe you're transitioning into cloud, you may have noticed that Cisco had something called NetFlow on their switches, on their routers, say 30 years ago, 25, 30 years ago. And what NetFlow would do, it would show you where your traffic was going from point A to point B so you could figure out your traffic flows. Fast forward 25, 30 years, AWS has something that looks just like NetFlow. They call it VPC flow logs. All your cloud providers do. And basically, it's going to give you information about the traffic going into your system and the traffic going out of your system. You can tie some of this stuff into your SIEM systems from a security perspective to try to correlate certain things. But also understanding where your traffic is going in and out can help you with a lot. It can help you size your applications, considering your network capacity planning, determine server sizing, but here's what else it can do. It can help you figure out when you broke something with your security. You create an overly restrictive access control list, network access control list, I promise you you're going to break something. If you're not careful, you create an overly restrictive security group trying to lock systems down, chances are you could break something if you don't know what you're doing. And determining where the traffic is going in and out of your systems and where it gets blocked is a wonderful opportunity for you to fix things that are broken before they become very, very broken. So what are you really doing? You're basically specifying the resource which you want to create the flow for, log for. You're going to tell it the kind of traffic you want. Do you want it to capture rejected traffic, like something that was blocked by your access control list or your security group? Do you want it to tell you the traffic that got through, or do you want to know all about all of that? Personally, I want to know about all of it. You have to tell it the destinations where you don't push the flow log traffic. Do you want to send it to an S3 bucket, for example? Where do you want to send it? So at the end of the day, what's this really going to look like? It's going to look something like this. You can see where the data is coming from. The count number is hidden here. The elastic network interface where we're learning it is here. The source address where it's coming from. The destination address, note it's a private address. You can see the port number. You can see the IP protocol that's used, the number of packets that are there, and the start and time. Note the first line is rejected. Something's blocked somewhere, maybe an access control list or a security group. Second packet is accepted. The next two are rejected. So if you're not able to reach something, you're seeing all these things that are rejected in your VPC flow logs, chances are you configured something that you didn't really necessarily want to. So kind of keep that in the back of your mind. So these are typically what we're talking about with regards to VPC flow logs. I'm going to talk a little bit about virtual private networks. And there's going to be a lot of different ones. And I believe, Benedict, this is you on the virtual private networks after the beginning. I think I introduced it and you get into the security, but if not, I am happy to continue. Benedict, just let me know in the box. Pretty sure when we get to VPN security, it's you. So Mo had talked about some other types of VPNs. And a VPN, in all honesty, is when you take a public network and you create a private network. There's a lot of VPNs. This is not new. You know, the ISDN networks, honestly, they created these little circuit switch patterns that we used years ago. You were getting a private line or a private connection or a private DS0 inside of a bunch of switches. It was a virtual private network. We had frame relay. They had these switched virtual connections. You didn't own the frame relay switches. It was a VPN. Then we had ATM, and we switched via cells. But again, it was a permanent virtual circuits or switch virtual circuits. Again, it was through a public network. That was a VPN. When you connect to AWS on a direct connection, and you send them a VLAN, and they segregate your traffic from everybody else's traffic based upon an 802.1q tag, it's a VPN. Now, when you connect with multi-protocol BGP and an MPLS-based VPN, and you've got virtual routing and forwarding instances, that's a layer 3 VPN. So lots of VPN technologies to talk about. But in this particular case, when we talk about VPNs, we're typically talking about IPsec tunnels and traditional what you would think of as VPNs. When I access your work at work, you access your office remotely from work, chances are you're connecting to an IPsec VPN. Potentially, you could be using a TLS VPN, which does work, but there's advantages and disadvantages to IPsec VPNs versus TLS VPNs. specifically as you can look at the flows of the data. So why on earth do we need to create this VPN? Well, think about it. The internet's not secure. So I want to go from point A to point B, and I know we talked about VGWs, but we're just talking a little bit about VPNs here. If we don't encrypt the data, it's not going to be secure. Now, what are we getting out of IPsec? We're getting actually a lot. We're getting three things. We're getting confidentiality, meaning people can't see the data. We're being able to authenticate the users and determine who the user is and who they claim to be. And we're being able to make sure that the person didn't send it. So, for example, Benedict's on the other side of this thing. I want to send a message to Benedict. I really want to know that Benedict is actually Benedict, as opposed to Hallie the hacker pretending to be Benedict, where I'd connect to Hallie the hacker instead of Benedict, and I'm giving information to Hallie the hacker instead of Benedict. That's called the man-in-the-middle attack on cybersecurity. With IPsec, we've got endpoint verification. We can make sure that we know who is whom. So I am connected to Benedict on the other end, not Hallie the hacker. Now, anytime we run encryption, we typically use a hashing protocol. And the hashing protocol basically runs a mathematical hash on our data. And anytime we put our data into a hash, it should come out the same on both sides. Put the letter A into a 256-bit hash, get a 256-bit response, etc. But you can't go from the 256 response back to the letter A. So by hashing the data and coming up with a mathematical hash, when I want to send some information to Benedict, I hash my data, part of my IPsec protocol, and Benedict knows that the message hasn't been changed. How important is this? Well, imagine a doctor that prescribed a medication and the medication dosage was changed by 10 times or 100 times along the way. Or when you tried to deposit $1,000 in the bank, somebody else stole it and they put a penny in your bank account instead. So that's the integrity that we're talking about. The last part of the IPsec protocol is something called non-repudiation, which means that I can't say that I didn't send it because there's a sequence number. Message 1, message 2, message 3, that sort of thing. I hope that makes sense. Benedict talked about the other reasons we're going to be using a VPN earlier. And why are they? He mentioned we can't put private addresses through the public internet. That would be another one. What if we had to push IP multicast across the internet, like Mo was just talking about? These are the reasons we're using VPNs: privacy and integrity. Now, Benedict, is this yours at this point? If so, I'll turn it to you. If not, I will continue to go. Okay, let's go. Benedict, let's turn this over to you at 97. Please do that with you.
Thank you. Thank you very much, Mike, for introducing the concept of VPNs. So now I want to talk about VPN security. How do we maintain security of our VPNs in the AWS cloud? Now, first of all, we have to understand that security is a shared responsibility when we talk about cloud technology. So there's that part of security that concerns AWS, and there's the other part of security that concerns the subscribers to the service, right? So VPN security is all about protecting the data that is traversing the VPN, and then creating policies to define who can modify, create, and monitor VPNs as well. All right. So imagine if an unauthorized user was able to gain access to your infrastructure and create a VPN endpoint, and then goes back home and sets up a router or a firewall on his end so that he could connect via VPN to your infrastructure. That would be very risky, right? So for VPN security, we want to have strong identity and access management policies that will define who has access to creating VPNs, modifying them, and going through the logs. So in essence, what we're doing is we're trying to enforce identification, authentication, authorization, and accounting. So VPNs use the IPsec protocol to encrypt traffic that is flowing through the through the tunnel to the destined location. The VPN provides confidentiality and integrity. How does it provide confidentiality? It encrypts the data in the VPN tunnel with a private key known only to the user, so that if it were intercepted over the internet, the threat actor would not be able to decipher the contents of the VPN tunnel. With regards to integrity, it hashes data that is flowing through it with a hashing algorithm, so that it can be authenticated at the other end when it gets to its destination. Because a hash is a one-way function and non-reversible, you can always tell if the contents of the data have been manipulated at the under end when you run the hashing algorithm and then you see the results. So it's also very important for us to monitor our VPN traffic and log traffic as well. I'm sure you're aware that there are some intrusion prevention attacks that can be encrypted, right? So when you notice anomalies in the VPN traffic, it could be a pointer that something is wrong. For example, if you set up your VPN for access from the 10.0 network to the web server, and all of a sudden you see VPN traffic going to the database server instead, it could be a pointer that there could be something going on with your VPN infrastructure, and that's something that you want to check and make sure it's all clean and good. Now, there's a little diagram here. I'll just show you. Give me a moment to share my screen. So just drag this here. So Chris, can you share my screen? Okay, so ideally in the AWS infrastructure, this is how your VPN setup would be. You have a virtual gateway in your VPC cloud where the VPN is going to be terminated. And on the other end of your VPN connection, you have what is called a customer gateway, which would typically be a router or a firewall where you can terminate a VPN connection. So it's a very simple architecture for setting up VPNs from our corporate data centers to the cloud.
I think we have some audio issues over there going on right now. A little bit of a tech issue going on. Benedict, while we get your audio straightened out, I'll take over in the short term. Chris will work with you in the back end on that audio piece. So going through this together, the reason that we're using IPsec is we're going to get through those security challenges. I really want you to think of the internet as a terrifyingly scary place. I want you to think about the need to do that encryption, as Benedict mentioned, the authentication of the peer. And this is going to be done with an internet key exchange to determine who is on each side. Benedict mentioned the hashing for message integrity, and we mentioned the non-repudiation, which is you can't say after the fact that you did something. So next, let's talk about VPN advantages. It is so easy to get a VPN set up, and here's what I mean. Do you have internet access at your house? Chances are you do. How many hotels do you go to where there's internet access? Coffee shops where you go to where there's internet access. There's almost internet access everywhere. It's fairly ubiquitous. Even my happy village in Greece, and there's not a lot of people in there, there is internet access everywhere. So as long as you have internet access, and the end of what you're going to connect to has internet access, you can set up a VPN. Now, will that VPN perform well? Who knows, based upon the performance of the internet, because there's no guarantees. But keep that in the back of your mind. Now, if I needed a private line, and we'll be getting into private lines, we'll call them direct connections. Azure would call them Azure would call them express routes. Google would call them a direct interconnect. In this particular situation, you know, we could do that. We could use a private line, but private lines, we have to get them. So I want a private line. I call my phone provider. If my phone provider creates the connection, and, you know, 3 weeks later, 4 weeks later, I can get my private line. VPN. I've got internet access. Cloud providers on the internet. A couple of configuration commands, and we'll keep it for the back of your mind. Simple, simple, and effective. So let's talk about the disadvantages of the VPN. There's no guarantee on the internet. And since there's no guarantees, we can't guarantee performance. We can't guarantee bandwidth. We can't guarantee that our traffic's going to get there. We can't guarantee latency. We can't guarantee what all those internet service providers along the way are doing. And there's no guarantee. So once your data gets on the internet, it's best effort versus a private line. I think Benedict's issues are back. So Benedict, I think you've got things taken care of on your end, and I'd love to go back to you.
All right, thanks, Mike. So let's talk about accelerated site-to-site VPNs now. Mike just mentioned that one of the drawbacks for VPN is that it's going over the internet, right? So there's no guaranteed bandwidth. You're constantly struggling with other users for traffic over the internet because it's not a dedicated link, right? Now, AWS has kind of a solution for that, or if I say a mini solution, and it's called the accelerated site-to-site VPN. And what's happening here is that it takes advantage of edge computing to route VPN traffic to the AWS global backbone, right? So it improves the performance of routing traffic through the AWS global network. Now, how does this work? So ideally, if you have a VPN connection between your data center and the cloud, and you do a trace route to see the path that your data takes from your office to AWS, you see that it goes over a number of hops, right? And this hop represents routers, firewalls of different service providers. And because you have different latencies, it creates a sort of bottleneck from your organization to the cloud. Now, what happens in the accelerated site-to-site VPN is that your traffic is routed to the closest AWS edge location so that it does not traverse multiple hops across different service providers to the cloud. So you have from your office, it goes through your primary um, service provider and onto the AWS edge location, then to the global backbone network, which is congestion free and which will help to improve the speed of the VPN connection. So it provides some improvement in VPN connectivity and traffic engineering for end users. So this provides a workaround to the inconsistent performance of VPNs, although it's not still comparable to a private link or, if you like, a direct connection to the cloud. And how do you set up an accelerated site-to-site VPN? It's just a box you check when you're configuring your site-to-site VPN, saying you want to use the accelerated site-to-site VPN, and of course, the cost implications for that. Now let's talk about network encryption options available on AWS. Earlier, Mo talked about SSL and TLS encryption and the important role it plays in protecting data, especially in transit, right? Data on the move. Now, there are encryption options available in AWS to help you enforce confidentiality on your data. TLS or transport layer security, which succeeded SSL, is an encryption protocol that we use to secure data in transit. So it's also used for protocols such as FTP, where you're transferring a large file from one location to the other. So FTP is the insecure version. And then when you add TLS to it, it becomes FTPS, which is secure FTP. And SFTP is another protocol that uses TLS encryption. Secure SMTP, which is SMTPS. These are protocols that employ TLS encryption to protect your data on the move. And these options are available in the AWS infrastructure. Now, the AWS Certificate Manager is another service that you can use to enforce encryption in the cloud. And how does this work? The Certificate Manager allows you to generate and manage TLS or SSL stroke TLS certificates in your AWS infrastructure. Now, ideally, if this service was not available in the cloud, you would have to go to public providers such as GoDaddy, purchase a certificate of them, import it to your AWS infrastructure, and then install it on your application, your web applications, or your database applications, or as it were, right? But AWS has something in-house, which is a certificate manager that you can use to generate these certificates and then apply it to your services as required. Another encryption option is the AWS Key Management Service, which is used to manage the keys associated with your certificates. So we have, I know Mo also mentioned a bit of the public key infrastructure, private and public keys. You need a service that can help you, generate these keys and manage them. The AWS Key Management Service, or if you like, the KMS service, allows you to manage your keys associated with your certificates. Now, applications such as the Elastic Load Balancer, CloudFront, and different gateways support TLS encryption from traffic that is flowing through them. So if you have a load balancer, for example, you could do what we call TLS offloading or inspection by the load balancer, so that traffic passing through them is encrypted before it gets to the backend server, because that feature is available in the AWS infrastructure. How about the network firewalls? They also employ SSL TLS encryption, and they need this service so that they are able to decrypt encrypted traffic that is coming through the firewall. So you could, there's a DNS attack where you could hide a malicious code in a DNS packet, and then send it through the firewall. And because that code is encrypted, it could go unnoticed if there was no firewall in place. But the firewall can use the SSL TLS decryption to inspect this encrypted traffic that is flowing through it and help you to keep your services safe and secure. So we'll talk about more encryption options available in AWS. Of course, we've spoken about the virtual private network. Now we have two kinds broadly: the site-to-site VPNs and remote access VPNs, or if you like, the client VPN, as AWS calls it. Now they use the protocol IPsec to encrypt the traffic that is flowing through them, so they keep it safe and secure from eavesdropping, right? Client VPN is a bit different, right, from site-to-site VPNs, although there are some solutions that allow you to use IPsec, the IPsec protocol on client VPNs. In such situations, you have to do it in software. So you'll be using maybe a software like 40 clients to implement the IPsec VPN, even if it's a remote access VPN, right? But ideally, the remote access VPNs or the client VPNs supports OpenVPN, right? Which is an open source software that they use to secure communications from the end user to the AWS cloud. Another network encryption option available on AWS is the AWS Transit Gateway, which Mo spoke about earlier. So you see that you are able to create IPsec tunnels from your branch locations to the transit gateway, so that you have some form of protection from the traffic from your branch locations to the other locations, right? So it uses IPsec encryption to secure this traffic. How about your direct connection or your private link? Now you would ask, it's a private link from your office to the cloud, right? It's a logical wire. Why do you need protection? Well, if you're employing a security in-depth policy, you want to trust no one, right? So even though it's ideally a private link or a secure connection from your office to the AWS cloud, you can still run IPsec VPN over the direct connection, So that's also another option available for network encryption in the AWS cloud. Now, we've been talking about data in transit. How about data at rest? Now, data at rest refers to that data which is stored in your drives, your S3 buckets, and so on and so forth, right? We have some options available in AWS to help you encrypt data at rest, so that if that infrastructure were compromised, the end user, the threat actor, would not be able to decipher the information, and it's useless to him. So it gives us that extra level of defense, as it were. Now, when it comes to data at rest, there are two concepts which are usually discussed. We have the server-side encryption and the client-side encryption, right? So what happens when you're doing server-side encryption is that you're encrypting the data on the server side. So in this case, you're encrypting the data on your S3 buckets, for example, right? For client-side encryption, you're encrypting the data on your endpoint, could be your PC or a server. You're encrypting it before you send it maybe to an S3 bucket. So it's like adding an extra layer of security for your transfer of data from your endpoints to your storage locations. For S3 buckets, they have what is called the server-side encryption with Amazon S3 managed keys, or what you, if you like, just share my screen here. So they have what they call the SSE-S3, which is basically server-side encryption, and is the default encryption method for Amazon S3 buckets, right? Now you have what you have, you encrypt your data with private keys, right? And you have the option to generate your keys in AWS and then encrypt the data, or generate it on-prem. Maybe your security policy has defined that you have to generate your keys in-house and not on the cloud. But you could import the keys and then use it to encrypt your data on the cloud. So those options are available. You have the server-side encryption with the AWS Key Management Service. So in this case, you are using the key management service in AWS to generate your key and then encrypt the data on your storage, your S3 buckets in this case, right? You also have another encryption option called the dual layer server-side encryption with AWS keys. Now, where is this applicable? Let's say in your organization, you have a policy that says you have to encrypt 2 times. You have to do, you can't just say, we're not comfortable with encrypting once. The dual layered server-side encryption allows you to encrypt data 2 layers in the cloud. So it gives you that extra layer of security. And then you use the key generated from your key management service to encrypt the data. That's why you have it called the dual layer server-side encryption with the AWS KMS. Then you have another option called the server-side encryption with customer provided keys. And this was what I talked about earlier. You could generate your keys on-prem, import it to the cloud, and then use those keys to encrypt the data on your storage, your server, right? So that will be the third option there, which is a server-side encryption with customer provided keys. And then I mentioned client-side encryption where you're basically encrypting data on your endpoint before sending it over the infrastructure, right, to your S3 bucket, right? So the traffic is encrypted end to end, so AWS cannot see that traffic as it traverses its network to the destination. And is usually implemented by downloading an Amazon encryption client to your endpoint, installing it, and it does the encryption before you move the traffic to the cloud. So let's talk about implementing network encryption methods to meet application compliance requirements. Now, so for many organizations, they have requirements. So if you're a financial organization, you have PCI DSS compliance requirements. If you work in a hospital, you have PHI requirements. If you serve customers in Europe, you have GDPR requirements, right? AWS has some solutions to help you meet these compliance requirements for your organizations, right? The first of them is the KMS encryption. So the KMS, Key Management Service, is a managed service that allows you to manage your keys, your private keys, right? It is integrated into services such as the S3 buckets, your relational database service, and your EBS volumes as well, right? So that you can just implement the encryption directly from those applications when you're working on them. Now, the Amazon Relational Database Service, RD, or if you like RDS, also has an encryption option available. So if if the IT governance personnel in your organization was concerned about encrypting data in the database on the cloud, there's a solution, and it provides server-side encryption for encrypting data at rest. So it allows you to use server-side encryption with the key management service provided by AWS. So what it means that you generate your keys for the key management service, and then use those keys to encrypt the data in your relational database in the cloud. And of course, we mentioned the S3 as well, Amazon S3, right? So it has those encryption options, dual layer, server-side encryption with Amazon keys, and then server-side encryption with customer-provided keys. We also mentioned earlier the AWS Certificate Manager, which allows you to generate and manage your SSL certificates. So, like I said earlier, it saves you that bit of going to a public provider such as GoDaddy to generate a certificate, purchase it, and then import it to your cloud. You could just do everything, manage the whole service from the AWS Certificate Manager. And it's integrated with services such as EC2 instances, so that you could just import a certificate and use it on your various applications in your virtual machines on the cloud. Now, there's also what we call the hardware security module, and it's a very important piece of hardware because it helps you to manage your encryption keys and perform operations on them, such as key rotation, deletion of keys, and stuff like that. And in some organizations, you find that it is contained in their security policy that they must manage all their keys with a hardware security module, right? Or if you like, a HSM. So is that not a problem for an organization trying to host resources on the cloud? Well, there's a solution. AWS has what's called the Cloud Hardware Security Module, or the Cloud HSM, which allows customers to manage their keys and perform those operations I talked about, such as key rotations and the rest of them. So if it's required by PCI DSS that you must use a hardware security module, well, AWS has it, the Cloud HSM. So there's no need to panic. Okay.
You know, Benedict, that might be actually a great time to end for the day. I'll show an encapsulation photo, and then tomorrow we can have fun and we can talk about high availability VPNs, and then we get into direct connection. You have to excuse me. I love anything with tech. I love anything related to networking, and I don't, as an architect, I focus on the business, so it's very rare that I get to get geeky like this. So for me, this is fun. Now, I promised a lot of you guys that I would show you encapsulation from my perspective. So I have a slide that I made for you that's going to show you encapsulation. So in order for you to understand my model, and Chris, if you can share my screen I'll share my screen real quick. So in order to understand my model over here, let's say in this particular case, I don't know what just happened there. In this particular case, I wanted to go into a building, and that building didn't allow cats. Well, I could just put the cat in the bag, close the bag, go in the building with the cat, and nobody'd be the wiser. So this is typically encapsulation. You put something into something else. No cats allowed? No worries. We'll put the cat in the bag. Now, bring it back to one other kind of concept. We also deal with containers in cloud computing, right? What is a container? It's like a VLAN, honestly, where you take in information, you put it in a containerized environment where it's separate from everything else. It's a form of encapsulation. Guess what? Here's another form of encapsulation. You put a cat in a basket, and the cat is now encapsulated. That is now separate or segregated from everything else in the room. So, not to do too many Cindy photos, but I wouldn't be me if there wasn't at least one cat photo coming somewhere. But honestly, I hope that explains what encapsulation is. Not allowed to bring your cat with you. Put your cat in a bag, carry the bag. Don't let anybody see what's inside the bag. It's encapsulation. With encryption, we could have envelope encapsulation where we totally encrypt the entire thing. We could just have encapsulation where we put something in another packet, but now you know what is encapsulation.
So in your example, would that be encapsulation?
It's encapsulation, absolutely. While we're
sorry, I couldn't help it.
That would be encapsulation. That is a great way to do it. So I don't know about y'all. I had some fun. Maybe you guys, if you had a good time, can like the video, subscribe to our channel, hit the bell to be notified. Send these videos to someone else that may have missed it, because we want to know that you guys get as much education as we possibly can. So if you hadn't gotten our labs, please download them. They're free. There's about a day and a half's worth now. We're going to have close to 2 days by the time this is done. Labs on AWS, labs in the data center, labs on networking is good. And we're going to take some questions too. But I just wanted to make sure you all knew that. So we're going to do some questions, whatever questions you guys have, a little bit of them. Then we'll finish for the day. We'll come back tomorrow, and we'll have all kinds of fun on this AWS Advanced Networking course to prepare you for the ANS-C01 exam. And this is our full AWS Networking specialty course. So let's see if you have got any kind of question. From Mohammed, over there in Somalia. I know where you're at, Mohammed. It's always good to see you. With Transit Gateway, IPsec VPN, and accelerator to connect by the nearest edge location by the client. I'm not 100% sure I understand exactly what the question is or the comment is. Do either you get that, Benedict or Mo?
I'm not really sure what is asking.
So I think I understand what he's trying to say. So what he's asking is a transit gateway IPsec VPN and accelerator to connect site by the nearest edge location. Yeah. So there's a feature on AWS. I think what you're referring to is the feature within AWS Transit Gateways where you can use basically the global accelerator infrastructure in order to speed up your IPsec connections. Yes, that's a possible solution you can use within a transit gateway, not with a virtual private gateway though. Only a transit gateway. I hope that answers your question. It's more of I think a statement than a question because I agree. But yeah.
I wasn't sure. I know Mohammed. He's very smart, but sometimes, you know, in a chat box, you're limited on what you can communicate. Sunday, you said we are awesome. Thank you so much, Sunday. We really are happy to be here and happy to help. Alex, thanks so much for this great session. Alex, thank you for being here. Sunday, you're more than welcome. We're thrilled to be here. Mike, I am giving you guys ideas how to get in trouble with cats where cats are prohibited. I like my cat. I try to bring my cat with me everywhere. And Ken or Grant, you are more than welcome. You're more than welcome. We look forward to seeing you tomorrow. The cat made me out. I'm the plan will fail. Ed, you are totally right. In fact, when I brought this cat home, it was to surprise my wife. And I called home and I'm like, hi, dear. How are you, love? And all she hears is, meow, meow. And she says, is there a cat with you? I'm like, I don't know. And then it never stopped. So, yep, my plan failed very quickly. It was not a big surprise. So, Joseph, these are not downloads. These are things that you can attach in our content management platform. It is there, and they will be available as long as they are current and running. So 6 months from now, a year from now, you should still be able to access them. 2 years from now, we want to make sure you have access to it. Saad, thank you, team. You guys are geeky and great session. Thank you so much. You're going to be awake in the next two nights ascending from Sydney, Australia. Prasad, I've attended U.S. things from Sydney, Australia, and thank you. I'm flattered you're here. I've also done it I've spent a lot of time in Brisbane as well and Melbourne where I got a lot of good Greek food, but Sydney's a beautiful place, so sounds great. Will we expand Cloud WAN?
Well, Cloud WAN is, I think it's its own topic. It's not part of the AWS exam. So that's really up to Mike and Chris. I'm not sure if we have time to cover it, honestly. But, if we have time at the end, then I guess we can.
Yeah, if we have time at the end, we can try it towards Sunday.
Yeah. Yeah, I would love to explain it. It's one of my preferred topics.
Okay. So, I want to thank you all for attending. I had fun with you guys. Hope you guys had fun. We will be back at 10 a.m. Eastern time tomorrow. All bright-eyed and bushy-tailed. The whole Go Cloud Careers gang, which is the three of us. There's a team of people behind the scenes. Mark's doing stuff to create content for you guys behind the scenes. We got lots of people behind the scenes, trying to work with questions and things like that. So guess what? You know what we're going to do next month for y'all? We're going to have a completely free AWS Solutions Architect Associate Bootcamp. What we do is we train careers, we train architects in our paid programs, but I don't believe and we get good results for it, but I don't believe anybody should ever have to pay for certification training. So we're going to have a very nice AWS Solutions Architect Associate Bootcamp coming at the end of the month as well. We'll give you sign-up forms that you can sign up to. So I want to thank Mo for sharing his many years of wisdom. I want to thank Benedict for sharing his many years of wisdom with you all. Thank you all for being here. And give me a hashtag, AWS Advanced Networking, and we'll see you all tomorrow. Take care, everyone. So nice to see you.
Thank you. Have a good day.